Good evening, everyone. We are in the week 5 of the course, Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. So this is the fifth problem-solving session or week 5, which is Frequency and Time Domain Digital Control Design Approaches. Let me share my screen. Can you see my screen?
Yes, sir, able to see.
Okay. So we are in the week 5, which is frequency and time domain digital control design approaches. The course is digital control in switch mode power converters and FPGA-based prototyping. I am Teja Golla, a third-year research scholar working under Dr. Santanu Kapat at EPML, Department of Electrical Engineering, IIT Kharagpur. So before we start, I just want to summarize what we have discussed in the week 4. So week 4, we have discussed about modeling techniques and model validation using MATLAB. So here we have mainly discussed about the small signal model, large signal model, continuous time model, continuous time with delay, and discrete time model, and their validity. So up to what frequency they are valid, all these things we have discussed. So now coming to the week 4 summary. So we are still in the week 4 summary. Small signal block diagram under digital control. So let me change the pen color.
Sir, I'm not still clear about the what is small signal modeling and large signal modeling.
Okay,
if possible, give
yes.
clarity.
Okay. So let me summarize, then we can discuss before we go into week 5. So let us assume that you are aware of the small signal, but I'll come to this point later. So we have first discussed about small signal block diagram under digital control. So first we have discussed about continuous time model, and then continuous time with delay, and then we have also shown the discrete time model. So what are the major differences? In continuous time with delay, it is exactly same as continuous time, and it is in S domain. So this is in S domain, and this is in Z domain. So S domain is the continuous time and Z domain is the discrete time. And then I have shown a few aspects like current loop stability analysis. One is the mixed signal. So for the loop to be stable, what are the aspects in the case of mixed signal or fully digital, what it has to obey so that the loop will be stable. That aspects we have discussed here. And then we discussed something about large signal DT modeling. So in the large signal DT modeling, we have discussed about the analysis. So we derived the equation, and then we have simulated and checked the validity, whether it is validated or not. So we have checked that it is validated because we have seen it is perfectly matching. So it was perfectly matching, which shows that our large signal DT modeling is accurate. Then coming to small signal DT modeling. So we have derived this large signal DT modeling in small signal DT modeling. So it has two methods. One is method 1 and one is method 2. So in method 1, what we have done, we have given some perturbations, and then we have found the perturbation, how it will get reflected. And phi is due to the state space perturbation, and gamma is due to the duty ratio perturbation. And then we have applied superposition. We have applied superposition theorem. And method 2 is the Jacobian method. So we have did partial derivatives. So, and this I can say Jacobian method because we are calculating the Jacobian matrix. And then we have checked the stability and loop transfer function. So whatever small signal transfer functions we have obtained, that we have used for getting the loop transfer function, and using them we have checked the stability as well as loop transfer function of digital voltage mode control and mixed current mode control. So we got two equations. So one is for the loop transfer function, and one is for the stability. So for stability, we will get in terms of Z, and loop transfer function is transfer function in terms of Z. This is the discrete time model. If you go with continuous time, it will be in S domain. So, and then model accuracy. So here I have discussed. So continuous time is for continuous time, and continuous time with delay, it will be in S domain, and it is sufficient for controller design. And we have seen that it is matching till Fs W by 10, which is sufficient for the controller design. And but it will be failing to completely give us the information regarding the stability. So for stability aspect, we need discrete time. So if you like continuous time with delay is easy for us to design the controller, everything. So this is only for controller design and not stability. So stability, you cannot use this model because it will fail to give the stability informations and everything. And this will be used for stability, and it would be difficult for us to design the controller using this. Why? Because it would be easy for us to imagine S domain, right? Say if I look at a pole, I can say that it is on the left hand side or on the right hand side, and it would be easy for me. So for that purpose, we are going for the controller design using S domain approach, and you can still use this to design controller, but it will be very like I would say complex for us to understand. As this is easy and it would be sufficient, we'll go with this method, but it will fail to give the information regarding the stability, for which we have to use discrete time model, and then we have ended up solving problem solvings. So maybe I can use this place to clarify your doubt. So there are two things. One is the large signal model. So what large signal model says is, say I'm considering the inductor current. I hope I am audible and you are following.
Yes, sir, you are audible.
Okay. So large signal, what we have done is, say I have taken a sample here. Using this sample, using the equations, I am getting an expression of this sample. So this is xn, this is xn plus 1. So what large signal model does is, it will give me expression of xn plus 1 in terms of function of xn and the input. Usually our input is only V. There can be a load source at the output. For the time being, assume there is no load source or current source. So we are getting xn plus 1 in terms of xn. So using that equation, x dot is equals to ax plus bu, and y is equals to c into u, or cx plus du, and d is 0, so c into x. So using these expressions, we have got this expression because we have considered different modes. So just to this delay is one mode, and until this point is one mode, this is one mode. So this is mode 2, this is mode 1, and this is mode 2. If you go back to that slide, so here matrices are a comma 0, here a comma b, here a comma 0. So using these equations with the corresponding matrices, we got xn plus 1. So why did we choose, why are we going for large signal model? Because in the case of discrete time, we don't have the enough and complete information, right? We only have the particular sample information. So if I know the sample information here, can I get the sample in the upcoming site? Yes, when you know the input and the present xn sample, we are trying to get the xn plus 1. So this is just a model which will give the information about the samples xn, or say xn is il and vc, right? So xn is iln at the nth instant and vc at the nth instant. So we are getting the information about the system, state variables, everything. So large signal model is to get these information accurately with ripple, because we are not neglecting the ripple, we are considering the ripple. So it will give us the information, accurate information, and then we have validated using MATLAB. So validated using MATLAB. So now until this point, we have got the large signal model, right? So we got the large signal model, and then we have validated, because whatever we are getting, whether it matches with the switch simulation, that I have to check. So this completes the large signal model. Now let me come back to the small signal model. So why do we need small signal model? See, whatever controller we are designing, we are designing the linear controller, right? So linear controller, which means it is designed around a equilibrium point, or you can say around some steady state equilibrium point, and you consider small perturbations. You'll consider small perturbation. So when we design, our system is non-linear system because of the switching, and we are designing the linear controller. So we have to linearize the system. So we have to linearize the non-linear system. NL means non-linear. So nonlinear system. So we have to linearize the nonlinear system, and around that equilibrium point, we design the controller. So the first point is this: the whatever nonlinear system we have, first we have to linearize it, and after linearizing only you can design the controller. So this is the linear controller, whatever we are designing. So the system has to be linearized. So whatever large signal model we have, it is nonlinear because you have seen it is a nonlinear function of xn and v. So we have to linearize it around that steady state. So what we are doing, we are giving a perturbation, and we are getting the xn plus 1 perturb in terms of xn perturb. So whatever equations that we got in the last week, so let me write with a different color. So xn plus 1 perturb, we got A equivalent into xn perturb plus B equivalent into D perturb. So duty ratio is one input and xn is another input. Now it is a linear system, right? So we have linearized the linear system.
Sir, during perturb, will there won't be like input voltage for perturbation?
No. One assumption that we have considered is input voltage is constant. So we have considered input voltage is 0, so V in perturb is 0. But if you consider input has perturb, then you will get some other matrix into V in perturb, which makes it complex. But whatever converter we are running, we assume that input is constant, more or less. So V in perturb we have considered constant because V in this V in perturb is considered 0 because V in is constant. Now we have linearized the system. I will not say linear system, I will say linearized system. So linearized system, because we are linearizing from the nonlinear. So now it is linearized. Now we can design the linear control. And how can I design the linear controller? One thing is we can get the loop transfer function. So we can get the loop transfer function. So how do I get the loop transfer function? For loop transfer function, I might need what in current mode control, GVC of S, and in voltage mode control, GVD of S. Again, these are small signal transfer functions. You should always keep in your mind whatever transfer functions that we are designing. Those are small signal transfer functions, because we have linearized it, right? Now it is everything is perturbed. So perturbed means it is small signal, not the actual voltage. So small signal transfer function. TF means transfer functions. So for designing the controller, we are considering the loop transfer function. And for this loop transfer function, I am trying to design a controller such that my desired bandwidth and phase margin are met. So that's why we are considering small signal model. And our small signal, I would say discrete time model. Discrete time, because I also want to know the ripple information, right? So that I can get the stability information as well. So for that reason, to get the exact stability and other phenomena of the converter, which I wanted to know. So I am designing the small signal discrete time model, so that this ripple information will be present in that, and I can get the exact stability information. Whereas in the case of continuous time, it is an average, right? Switch averaging method, or whatever method they are using, it will not contain any ripple information, no ripple information. So we are losing the ripple information. That's why. So one thing is, this is not accurate. So whatever continuous time delay, it is not exactly accurate, I would say, but it is accurate till, this is accurate till FHW by 10. And this is the bandwidth we consider usually for controller, right? So within our controller bandwidth, whatever we are planning to design it for, it is valid, continuous time with delay. So this one we use for controller design, but for stability, this will not work for stability. So for stability, we have to go with the small signal DT model. So that's why we are deriving the small signal DT model. But if you
why for stability, for why stability continuous time model is not able to work?
Yes, say Sar was discussing about some subharmonics, right? So if I say subharmonics, say it is like this. So say this is one kind of subharmonic. From here to here, it is one cycle. From here to here, it is another cycle. So it is not actually happening like this, right? It is repeating after 2 cycles, and I can see there is a subharmonic of FHW by 2. So it is it is not harmonic, it is subharmonic, because the frequency is a fraction value. So now it is happening in the say ripple. If I consider continuous time with delay, it will average out the ripple and it will give me an average value. So continuous time with delay is like an average value, right? So if I consider the average value, then I'll miss this subharmonic information. It will not capture this. It will be only captured by the DT model. Say if you consider large signal DT model, which where we are considering the samples. So if I consider large signal DT model, it will give me a sample here, and it will give me a sample here, and it will give me a sample here, and it will give me a sample here. So here, large signal DT model, we are actually considering the ripple information. So it will be able to capture this. Similarly, small signal DT model will be able to capture this. So continuous time with delay cannot capture because it is an average method. We are neglecting the ripple and we are considering the average. And there might be such case where the model says the system is stable, but there might be some subharmonics which will not be captured by the continuous time delay, for which we need the DT model. As far as controller designing is concerned, this is okay. Have you understood?
Yes, sir. One more thing I want
Yes. Hello.
to know is like how the green color
Sorry, your
and
voice is
what might be the
breaking.
reasons for get. Hello,
Hello, your voice is breaking.
still breaking, sir.
Now it is fine. Yeah.
Sir, what are the reasons for getting hello?
Yeah. I can hear you. Continue.
How like perturbations in the XN are generating, sir?
Okay, so say I'm giving some transient response. Then say maybe I can use this way. Say I'm giving some transient response, or I have given some step response. So for the new steady state, my IL and VC are different, right? It doesn't have to be the exact. So IL dash and VC dash. So my IL and VC are changing, for which the controller has to respond accordingly. So this perturbation in the IL and VC has to be taken care of by the controller, and it has to act accordingly. So the perturbation is coming, say, from a disturbance, noise, or actually you want a load transient. That is a perturbation, and for which we are designing the controller so that it can reach the steady state in our desired way. For we are using bandwidth and phase margin. So for that we are designing. So perturbation, if it is noise, it has to attenuate it, right? So if it is a noise, then the controller will attenuate that noise or whatever disturbance. But if we are giving it the new steady state value, say I am increasing from X amperes to Y amperes. So accordingly, the controller has to change so that this IL present X and steady state value, it has to go into the other steady state value. So I talk in terms of equilibrium point. So from the present equilibrium point, it should go to the new equilibrium point. So the controller will act accordingly. Understood?
Sir, will the like small signal modeling be able to work in the transient conditions too?
Yes, actually it is not like designed for very high steps, but as far as small steps are concerned, it is okay. But still there will be a limitation in small signal model because it has less bandwidth, for which we should go for large signal tuning. So that SAR has discussed in this week in the upcoming like around 47 to 50 SAR has discussed the large signal methods, where we will actually consider the trajectory. So in our large signal, SAR has considered something called trajectory base, which I will be discussing today also. So there SAR has considered from which I01 to I02 the current is changing. So accordingly, SAR is deciding the deriving the expressions and designing the controller. But our small signal works on the perturbation, so we are not considering very big step changes. So we assume that the perturbation is small, and that's why we are linearizing the controller. And yes, of course, we are thinking that perturbation is small, and hence when we give large step response, it might not also capture accurately. So for which we have to go for the advanced controller techniques. But as far as our small steps are concerned, it should be fine.
Okay, sir.
Sir,
Yes.
sir, in the large signal model
Yes.
of the the previous slide that you have marked that xn and xn plus 1. Actually, you said, oh, this one.
Yes, this one, right?
Yes, sir.
Yeah.
Sir, in our the large signal model is applicable both for transient as well as steady state.
Yes, yes. So large signal model is
but-
nothing but actually the switch simulation, but instead of getting the entire information, we are only getting the sample.
Okay. Sir, but in actually this equation, this xn plus 1 is a way of predicting from the value of xn and vn.
Yes.
It's kind of predicting the value xn plus 1.
Yes, like say I know the Wien matrix and I know the present state of the converter. I know the converter. So like whatever, see, if you consider MATLAB, how will it solve? So it is a mathematical model, right? So MATLAB, how does it solve? It is some mathematical model. And we are giving inductance, capacitor, whatever, like however way we are connecting it. So it has, there should be some initial value, right? So we are giving some initial value. And from there, it is using the mathematical models that they have developed. And the converter is running. So whatever simulation is concerned, they are also using some mathematical model, but their model might be considering some other extra dynamics also. But we are also using some mathematical model, whatever way the converter is supposed to work. So I know that it will be triangular waveform and it has 1, 2, 3 different regions. One is mode 2, mode 1, mode 2. So I am using this and I know how the converter is working. So I am using the actual equations, the state space equations, and I am getting an expression of xn plus 1. So I know that, so what I know, if I give this initial condition to my buck converter for these operating conditions, I know that at xn plus 1, this will be my inductor current, because the equations are saying, which will be again used by the MATLAB in the Simulink model. They are also using some mathematical models. You understood, right? Rajshekhar?
But sir, will this be working on the transient state also when the inductor current has not reached the steady state?
Yes. So it should work, because say we are giving the transient. Accordingly, we are changing our matrices, right? Say R matrix, sorry, not R, resistor. Resistor is V0 by I0, right? Say I'm giving a transient, then R value will be changed from R1 to R2. See, this we have to feed it to the code. The code will not know that load like step response is happening. We should tell the code that R has changed from R1 to R2. So when you see in SAR's code, SAR has 2 parts. First part is for R1 and second part is for R2. So SAR is changing the R resistor value to R1 and R2, and then SAR is calculating the AB matrices again, and then SAR is using the model. So the code will not know that there is a transient. We know when we are giving the transient. So we are calculating all the matrices and we are feeding it to the code, and the code is matching. Like the code is not predicting, the code is just showing the this sample and this sample, provided we are giving it all the information about the AB matrices, the conditions, everything. So if there is a transient happening, if we do not write in the code, then it will not detect, because the code should know what is happening. So if there is a transient happening, you should write that in the code that at this time the transient is happening. But if you tell it, yes, it will match. Is that clear?
Sir, yes, sir.
Okay.
So similarly, in this small signal model,
yes,
we are linearizing the system around the steady state point.
Yes.
Or around a point.
Yes.
So while we are trying to design the controller for that particular operating point, if suppose the operating point it changes, that is when the xn or matrix changes, A changes, then will the controller work for that change also?
Yes. The controller, we are designing the controller to work for that thing, right? Say maybe I can use this space. I am considering here V reference button. and this is plus minus. Here V not perturbed, and here the controller is there. And assume the all other matrices I have mentioned in some G plant of S. And this V naught is coming from here. Say I have given a reference transient. So what happens? This perturbation will change, right? So initially V reference is say 1 volt. Now I have made it to 2 volt. So V perturbation is 1 volt. So now there will be an error here. So error will increase. So GC will try to change its output accordingly, so that V naught perturb, initially it was 0. Now it changes to 1. So V naught perturb becomes 1, and then error becomes 0. So our controller ensures that the error is 0. So if there is any change in the say V ref or I naught, then accordingly it will try to reach that new steady state. Understood?
Yes.
Okay.
Hello.
So yes, I hope all doubts are clear. Yes, someone is talking.
Yeah, is it audible?
So, sorry, actually your voice is very low. Can you speak loud?
Hello.
Yeah.
Now it's okay.
Sorry.
Hello. Now it's okay.
Yes.
So every transient response, the equilibrium point will change according to the
Yes.
right. So based on the perturbation, suppose at a time 2 perturbations comes, if you change the reference as well as the duty cycle.
Yes, it will still be detecting, but only the transient response we are not considering while designing the mask, right?
So we don't doesn't have a fixed equilibrium point based on the changes. The
Yes.
equilibrium point.
Yes.
My question is how that equilibrium point is general. Any general rule or trivia, a rule of thumb, like this equilibrium point should be stay like this.
No. Like we usually consider that perturbation is very small. So and on top of that, we'll design.
So one doubt actually, what is that accurate till FSW by 10 continuous? When you use continuous time with averaging, with delay, it will be accurate till FSW by 10.
Yes.
Or like that.
Yes. So this is an approximate model which will be accurate till FSW. So this we have tested using Bode plot.
Okay. Oh. So that's why we are going for discrete instead of
Yes.
get more accurate.
Yes, but this would be sufficient to design the controller, but not stability. So for stability, we have to use small signal model, small signal DT model. And for controller, this should be enough, because this would be easy for us to design a controller. That's why we are going to this. Doesn't mean you should not use this. You can use this for both controller.
Here also we'll use small signal, right?
Small signal model, perturbation.
Like small, here also you'll use small signal.
Yes.
But for controller purpose, this continuous delay will be better. But for stability, you'll go for small signal DT.
Yes, I would not say better. I would say easy for us. So controller designing would using this would be easy for us because we are habituated with the S domain. Z domain is much more accurate, but till FSW by 10 we saw that accuracy is same. If accuracy is same, why should I go to this method? Because this is easy method for me. So I can use this. But if you want the exact stability, then this will not work. For stability, you have to use this method. So we are just checking. Yes.
How we are saying it is easy or like
easy, because say S domain, it would be easy for you to say, I would say S plus A by S minus B. Then I can easily say that the B is on the right side and the system is unstable. Whereas if I get some Z minus 0.5 plus J 0.6 by Z, Z plus.
You're saying discrete is easy.
No. I'm saying S domain, continuous domain is easy for us because we are more habituated with this.
It's not accurate. It's not accurate for whole. Only for accurate for FSW.
Yes, FSW by 10.
So that's why we are going for small signal DT. So for controller distance, it's continuous is better.
Like easy, I would not say better.
Okay, easy to design.
Yes.
Okay. From the equation, you can say which is pole, which is zero, whether it is right off or left off, like you say. I understood. Yeah. But in Z domain, we can't visualize. So
yes, exactly. We cannot visualize it. In S domain, it would be easy for us to visualize all root locus, everything. We do it in S domain, so we can. And also the frequency.
One basic question: what is the use of state space actually?
So state space, it actually predicts the dynamics of the converter. So
system
state space, yeah,
converter.
whatever converter
Yeah.
or system. So using this, we can predict the dynamic of the system. So it is more like we are modeling the system. So I have given some buck converter. So I can
Yeah,
say
yeah.
inductor current and capacitor voltage are states, and we are just getting the relation.
Okay, fine. So one last question. This
Mhm.
loop transfer function will get the small signal transfer function.
Yes.
That transfer function will give our required bandwidth and required phase margin what we
Yes.
have decided. So if we have set a phase margin of 60 degree from the small signal analysis, the transfer function will give a phase margin of 60 degree
Yes.
kind of thing, right?
Yes.
So
Yes.
that controller will deliver.
Yes. So in the loop transfer function, GC is the unknown. So I have to find these unknowns, provided I need this much bandwidth, this much phase margin. I have to find what is the GC value. So
So, like loop transfer function in the sense like the denominator will be poles, will GC will be the numerator, like
yes,
pole
yes,
zero cancellation.
that we'll discuss today. And there
Yeah,
is
yeah,
less,
fine, fine.
yeah, there is less than a minute. So
Yeah,
if
fine.
this meeting ends, please join it again so we can start the discussion.
Yeah, okay, fine. Thank you. Okay.
So week 5 is all about digital control design approach using frequency and time domain. So I'll quickly give an outline. So first we'll discuss continuous time to discrete time transformation. So which transformation should we have to follow? So we'll discuss three. One is forward, one is backward, and bilinear. So which one should be followed? Which one is good for us? We'll discuss about these aspects, and this is very conceptual, and maybe I'll spend some amount of time so that it will be very clear to you. Then we'll discuss two controller design aspects. One is the PI tuning of voltage mode control. Is my screen visible?
Yes, sir, visible.
Okay, so today I'll discuss about two controller design. So before I start, I just want to make it clear that so today I'll be discussing about only Buck, both only Buck. So if you want to ask queries about Boost, so there is another session tomorrow. So from 6 to 8 p.m. So that person will be discussing about Boost. Both are actually similar, but Boost, there is one additional RHP0. So if we have RHP0, how to tackle all those things. So today I'll be discussing about Buck because it would be difficult for me to discuss both in a single session. So we have broken into two parts. One is Buck and other one is Boost. So today we'll discuss about voltage mode control of Buck as well as current mode control of Buck. And first I'll discuss with the analog tuning, just a recap, because you might not have gone through the previous course. And then after that, we'll discuss about the digital voltage mode control PID tuning. Similarly, here analog first, digital. By digital, I mean mixed signal. So here, not fully digital, mixed signal current mode control. So then if you want, maybe we can show some, I can show some MATLAB simulation depending on the time left. And then we'll go into the last signal tuning and how to actually improve the transient response, all these things we can discuss. If time permits, we can solve few problems. Again, these problems will be from the concepts that we have discussed today. So coming into our first topic, which is continuous time to discrete time transfer functions. So transformation, not transfer function, sorry. So why do we need continuous time to discrete time transfer function? Because say if we have any transfer function in continuous time, if we want to change it into discrete time, say from g of s to g of z. So there are many transformations available. So one is the forward difference, or the other one is the backward difference, and the other one is the bilinear transformation. So which one we should use and which one we are using to implement the controller. So all these aspects we'll discuss in this session. So coming into the first thing. So this is what KIECYS.
Continuous time.
Integrator.
Yes, it is an integrator in continuous time. So the input is V error of t, and only integrator is the say the transfer function. Output I am getting ui of t, and the function time domain is KIC, the gain into integrating from 0 to t V error of t. So this is the error. So this is my continuous time, which is CT. Now coming to the discrete time. So in discrete time, I am doing the sampling, right? So I am doing the sampling So I will not get a VE of t. I will say get VE star of t or VE of n. That is going to my digital controller. And it is giving me output. So this is sorry, VE of t. So we are sampling in terms in the multiples of sampling time period TS. So we are getting VE of k, and that VE of k is fed to this digital controller, and you are getting UI. So if we discuss about the sample, so we know this is VE of t, right? So this VE of t is this red curve as they have shown here. So we are taking samples in the multiples of TS. So we are taking the sample here, we are holding it. We are taking the sample here, we are holding it. We are taking the sample here, we are holding it. We are taking the sample, we are holding it. So this is what VE of k minus 1, and this is VE of k. Right.
Then what is that symbol in the t-axis? Like there are two lines.
So
What
this
is
means
that?
this means it is not continuous. So you can consider it some amount of time. So after TS, k minus 1 TS is not happening. So this is repeated for some amount of time, and then k minus 1 TS instant is happening.
You are saying that it is not immediate. Like,
Immediate, yes.
that's the
After
thing.
some time,
Okay.
like it is there for
Okay, sir.
an amount of time. After that, we are getting this.
Okay, sir. Thank you.
Yes. So UI of t is 0 to t. Say t is NTS. So from this, I am getting this expression. So t is nothing but NTS. So from 0 to NTS, I am writing this. Why I am writing this? Because I want to kind of digitize it. So that's why I'm writing in the multiples of TS. So say t is from 0 point to the last point NTS. So this is in the continuous time, right? So I'm writing the same equation. And after that, I'm writing this as a summation. So I am breaking say 0 to NTS is there. I am breaking it into n different parts. So the first part is 0 to TS. The second part is TS to 2TS. The third part and up to so on n minus 1 TS to NTS. So how many I'll get n. So I'm writing this as a summation. So integration of this, say this is I1, this is I2, up to so on IN. I am adding all this I1 plus I2 plus up to so on IN. So I'm writing this in terms of summation. So why I'm writing in this summation? Because I know, say this I'm getting from the continuous time. Whereas in the case of discrete time, V of tau from k minus 1 TS to KTS is constant, right? So that's why I'm writing in this format. And for the time being, this entire expression,
Hello.
let us take it as Ik of tau. So is it clear till this point? Yes.
Can you repeat it once again?
Sorry.
Can you repeat it once again?
Yes, yes. So IC from 0 to t, V of tau d tau is there. So I am integrating it from say 0 to NTS, which means t is NTS. So I have integration. I'm writing this as a summation of integral 0 to TS into V error plus integral TS to 2TS into V error plus up to so on integral n minus 1 TS into NTS into V error. So this integration I'm writing it as a summation. So summation of integral some k minus 1 TS to KTS. Why I am writing this? Because this is in continuous time. If I change it into discrete time, V of tau from k minus 1 TS to KTS is constant, right? We are holding this value. So that's why I'm breaking in terms of TS multiples. So is that clear till this point? That's why I'm writing in this format. So in the upcoming slides, yes, yeah, okay. So in the upcoming slides, we'll discuss about three methods. So one is backward Euler's method. The other one is forward Euler's method. And before we going into backward Euler's method, so what backward Euler's method says, say we are considering Ik of tau. Ik of tau is what? Integral k minus 1 TS to KTS into V error of tau d tau. So integration is what? Area, right? So from this region to this region. So backward Euler will take instant at V of k, and we'll consider this area. So this is one possibility. So you may ask, sir, why are we taking this sample? I mean, why are you taking this sample? Why are we not taking this sample? So that is also another possibility, which is the forward Euler's method. So for forward Euler's method, we are taking this sample and we are taking this entire area. Because we are taking the this point and we are considering it backwards. So this is backward Euler. And we are considering this point and we are taking it forward. So this point is, we are assuming that it is being continued. We are taking it forward. So that's why this is a forward Euler's method. So here ik of tau, this is our ik of tau, right? So here ik of tau is nothing but VEK. So this is a rectangle. So you can consider this as length and this is breadth. So VE of k into TS. Sorry, this is L and this is B. So VE of k into TS. So the area of this is VE of k into TS. So this is VE of k, this sample. And here VE of k minus 1, right? So VE of k minus 1 into TS. So here this is the length and this is the breadth. So this is one possibility. Another possibility is average of both of them. So that is what Tusting's method or bilinear transformation method is called. So we are neither taking the sample, not taking the sample. Instead, we are taking the average of this. So average of this is summation of this sample plus this sample by 2. So this is 1. Excuse me. So 1 plus 2 by 2. And the area is the magnitude into time period TS. So here this is the length and this is the breadth. So these are the three possibilities of considering the area for this ik of tau. So we have considered three different possibilities. So backward Euler method means ik of tau is VE of k into TS. This is VE of k minus 1. And this is the summation of both by 2, which is the average. So now coming, so first we'll discuss about the backward Euler's method. Then we'll go forward Euler. Then we'll go into the bilinear transformation. So this is KIC into summation of IK, right? So KIC into summation of IK.
So this IK,
yes.
IK is the area under that curve, right?
Yes, area under that curve. So now what I'm doing, KIC into summation of IK. IK is what? VK of T into TS, right? So this is IK. I am getting from here, backward Euler's method. So I'm substituting it here. Now I got what? Ki into summation of k equals to 1 to n VE of k into TS. But what I am doing Ki as KIC into TS. So I have defined one Ki, this one, which is KIC into TS. So now it will be Ki into summation VE of k. So Ki, I have considered KIC into TS. Now, so let me do something. So UI of n, say UI of n is Ki into summation of k equals to 1 to V of k, right? So what I will do, I will take one term outside. UI of n is equals to Ki into V of k plus summation of Ki into k equals to 1 to n minus 1. So this is V of n. And now this is again V of k. So what I have done, I have brought the V of n term outside. Now what this will become? This will become Ki into VE of n plus this entire term is what? Ui of n minus 1. Do you agree? I have just taken out the nth term outside and I have written it in iterative form.
Yes, sir, agree with you.
Yes, so this is this equation. So why I am writing this equation? Because if I apply Z transform, I will get Ui of Z is equals to Z inverse into Ui of Z, because Z inverse is coming because of this delay, plus Ki into V of Z. Now if I write from this expression, if I write Ui of Z by V error of Z, what I will get? I will get Ki by 1 minus Z inverse. So I have written in an iterative form so that I can apply Z transform and I will get the whatever transfer function that is necessary. So I got this transfer function. So from this we are applying Z transform and we are getting this transfer function.
Like, sir, I understood how you made it into iterative form. That's
Yes.
fine. But how you are linking that iterative form to this transfer function?
So,
Could you please let me know that?
so in Z transform, if ui of n is ui of z, and for ui of n minus 1, it will be z inverse into ui of z. So this is
Yeah,
the
yes.
property of Z transform. So this is ui of z, this is z inverse into ui of z, and this is ki into v of z. Now I am doing some manipulation. If you bring this, bring it this side, you will get this expression finally.
Like
Okay.
for the transforming
this-
into Z transform, you iterated it, right?
Yes, I have written in an iterative form so that it would be easy for me to get the transformation.
Okay, sir. Okay.
Okay. Now what I'm doing? So if I realize this in a block diagram, I will get this.
Now this is the
Yeah.
sir. Now this is the controller transfer function, integral controller transfer function using backward Euler's method.
Yes.
This
Yes.
one.
So yes.
U
No, so
is z by v is
yes. So this is that integrator. We have considered integrator. So integrator transfer function in Z domain, using backward difference method. So first we are considering the backward Euler's method or backward difference method. So I got Ki into 1 by 1 minus Z inverse. So Ki I have put it here, and I have considered a positive loop because 1 by 1 minus means positive loop. So 1 by 1 minus Z inverse is just the representation in block diagram. So this you can do it, it is easy. So this is all about backward difference. So backward difference, we have this transfer
Hello.
function. Yes.
Okay, I understood this mathematics. Why it is called backward Euler? You're
Yes.
taking
So,
sample from the back side, or like
yes, yes. So we are taking this additional point and we are bringing this sample backwards, right? Like we are
so
considering
you're
this
taking
point and
KTS. We are considering KTS.
and we
Uh,
are bringing it backward to, like we are extrapolating it backward, right?
okay, so you're iterating in the form of un minus one. So that is the backward one.
Yes. No, no, not this one. From the sample, we are taking the future and we are extrapolating it backwards. So that's why it is
Okay.
backward. Now, if you go into the forward, I'll show you. So in the case of forward, we are taking this point and we are extrapolating it forward, right? So in this direction, we are extrapolating. So that's why it is forward. It is also,
Hello.
yes, yes.
What is that blue color dotted line and red color dotted line? Red color is continuous function. Blue color is
Red color
discontinuous.
is the continuous function. So red color, so this is the red color. So this is the red color. This is the red color. So
Okay.
after that, we are sampling it, right, at the interval of TS. So this is the blue color.
Okay, fine.
So we are taking the samples. That's why we are taking the sample and we are holding it.
So now we are taking the samples when the points which is coinciding with the continuous one and this one,
Yes,
right?
yes, yes. And now
Like
we
we
are
are taking
considering
the
this again.
V of t after sample and hold. The 2 points coincide at one point that you are taking as sample.
Yes.
Okay, okay. So if you have introduced a delay or like taking before, suppose
Yes, yes,
the
yes, yes.
came.
For the time being, we are neglecting delay. So this is ideal case. If you consider delay, then also the time period will be TS,
Oh, okay,
because it will be K minus 1 TS minus the delay to KTS minus delay. So effectively the difference will be still TS.
okay, fine.
So in this
Okay, good.
case, this is not V of K, this is V of K minus 1, because we are taking V of K minus 1. So there is a mistake. I'll modify it after this session. So V of K minus 1. Again, we are considering Ki to be KIC into TS. So what
Sir,
difference?
please,
Yes.
sir, could you please like V of n minus 1 y for nth interval, like nth interval in the sense n minus 1 ts to n ts, where we are considering n minus 1 sample.
Yes.
That's the thing you
Yes. Yes. Yes.
made use of. Okay.
Yes. Yes. So the only difference is here we are taking V of K because we are taking the point and taking it backward. Here we are taking this point and taking it forward. So here it will be V of K minus 1. This is the only difference. Now everything is same. If you go here, we will get V of N. But
Hello.
here we'll get V of N minus 1. Yes.
Uh, can you should go to the before figure?
Okay.
Not the backward Euler. This is only small portion of area is only taken. Or this
Yes,
part will
yes,
not be taken.
yes.
Uh,
Only this area is taken.
why that part is remained unlifted, or like it's
Because
any reason?
you are sampling it, right? So if you take this
Uh,
sample, you will get more area. If you get this sample, you will get less area, because that is what discrete time means, right? Because we will miss the information in between.
okay, fine. So
So
that's why
either
you're
we can
going
use
for
this.
forward Euler.
Yes, either this or that. So we'll discuss the advantages and disadvantages of each method, but we are trying to get the transfer function currently. So this is taking V of k, because of which we are getting V of n here. This is taking V of k minus 1, because of which we are getting V of n minus
Sir, could you please explain me like for a 0 to TS interval, which sample is taking in forward Euler and the backward Euler,
1. So
please?
in 0 to TS, see, forward means what? We are taking
Like,
the bottom one. This is forward.
yes,
So it will be V of 0. And for
yes,
backward, we are taking TS. So it
yes,
will
sir.
be
It is
V
V
of
of TS.
or 1.
Yes, for this it is clear. Like for for the summation term, I'm missing the point.
Summation k equals to 1 to n. V of k means it is just a summation, right? So V of 1 plus V of 2 plus up to so on V of n. And summation k equals to 1 to n. V of k minus 1 is V of 0 plus up to so on V of n minus 1. So here we'll get n minus 1, here we'll get n. So because of this, you are getting n here in the backward and n minus 1 in the forward.
Like, sir, if I'm having just only 0 to TS sample I'm having,
Yes.
then how my sigma notation will be there, sir?
There will not be any sigma,
For
right?
0 to
Sigma
TS.
is more than 1. If there is no sigma, you will have only one term. Like say, ki sigma k equals to 1 to 1 means there is no meaning of sigma. And V of k, then it will be k into V of 1, right? So if sigma is more than 1, if there is 1, there is no point of sigma.
Yes, sir. Like
Sir, in the
here, if
diagram,
we are having sigma,
Uh,
like at least we are having 3 samples, right? If we have at least 3 samples, then
two,
I
two.
only have to use sigma notation. Is that the point?
Yes, yes, yes.
Okay, sir. Okay.
Okay. So here we'll have n minus 1. So if I apply Z transform again, Ui of Z is equals to Z inverse into Ui of Z plus Ki into V of Z into Z inverse. So if I get the final equation, Ui
Sir,
of,
could you please explain that sigma notation for this method, please?
okay, let me write the expression that I have come here. So it will be Ki into Z inverse by 1 minus Z inverse. Okay. So in the case of backward Euler, I'll be getting V of k in the k minus 1 to kth interval. Whereas in the case of forward Euler, I'll get V of k minus 1. So in the case of summation, I'll write V of k, because of which I'll get V of n here. In the case of forward Euler, I'll write V of k minus 1, because of which I'll get V of n minus
No, sir, not clear.
1. Is this point clear? V of k into Ts, V of k
Yes, sir,
minus 1
that
into
is clear.
Ts. So for k minus 1 Ts to kTs, this is my thing, right? And
Yes,
this
sir.
is from k minus 1 Ts to kTs, V of k minus 1. So I am writing summation of it. So from k minus 1 Ts to kTs, it is V of k. So here I'll get V of k. And if I do this procedure, if I bring the topmost term outside and if I write it in an iterative way, I'll get a V of n. And in this case, I have V of k minus 1, because this is what I'm getting from this point. So V of k minus 1. And if I again write it in the iterative form, because if you substitute n, what is the maximum value here? Maximum value is v of n minus 1. So because of which the maximum value is v of n minus 1. And if I apply Z transform, I will get this additional Z inverse, which is
Like
not there here.
So here similarly, if you write this v k minus 1, the top term separately,
Yes.
are we writing that? If we,
Yes.
then it should
Again,
become k
we are
minus 2.
separating the top term. So from this point, I'm separating the top term, and then I'm writing the other terms as summation.
So it should be k. Then that summation term, if you're separating k minus 1 separately, then the summation term should come as k minus 2, right? Or k.
sir, that's we are feeling confused. Like ua of n minus 2, we are thinking, but actually
I'll
that
write
the point might be there will be
ui
n minus 1 terms, right?
ki into sigma k equals to 1 to n be of k minus 1. This is my term, right? So I'll take
Yes.
the topmost term ki into v of n minus 1. Now plus ki into sigma k equals to 1 to n minus 1 v of k minus 1, right? So this is n minus 1, which means this is ui of n minus 1. So my final term is ui of n is equals to ui of n minus 1 plus ki into v error of n minus 1. That is what I have written. So I suggest you to do it again, because if I teach you, then you are not writing it by yourself. So then you will not know. So I suggest you to write it again, maybe after this session. Then you will know.
Okay,
So
sir, sure, we will.
Yes.
Okay.
So because of this Z inverse term, we are getting this Z inverse extra term. Whereas here, this Z inverse is not there. We are getting K by 1 minus Z inverse. So here we are getting K into Z inverse by 1 minus Z inverse. So I suggest all the students to derive all the equations that I am discussing. So these are explained by Sar as well. So maybe after this session, I request you to do the derivation of all those things. Then only you can understand better. If you only listen, you might not be able to actually understand it. So I'll explain, but if you have still queries, I suggest you to do it by yourself. So this is ki in ki by 1 minus Z inverse. So this is this part, and this is the additional term that we are getting. So because of the forward difference method. Now, in forward difference method, we have v of n minus 1. In backward difference method, we have v of n. So if I go back here, so if this has v of n, and if this has v of n minus 1, so what will this have? This will have v of n plus v of n minus 1 by 2, because it is the average of both the things. So if I do that, so I'll get this expression. So v of n minus 1 plus v of n by 2. Again, if I apply Z transform, I will get ui of z is equals to Z inverse of ui of z plus ki by 2 into Z inverse plus 1 into v of z. I'm just applying Z transform and I'm writing the final expression here. So I will get ui of z by ve of z is nothing but ki by 2 into 1 plus Z inverse by 1 minus Z inverse. So apply Z transform and I have written it as an expression. So you will get this expression. Ki by 2 into 1 plus Z inverse by 1 minus Z inverse. The same can be applied here. So this term is what? This is 1 plus Z inverse term multiplied by Ki by 2 multiplied by 1 by 1 minus Z inverse. So 1 plus Z inverse into K by 2 into 1 minus Z inverse. So that entire thing is the Gi of Z for bilinear transformation or Tustin transformation. So we have discussed till now 3 methods. One is forward, backward, and the other one Tustin or bilinear transformation. So now coming to the comparison between these three. So let me use a different color, maybe black. So in case of continuous GI of S, what is my integrator? KI by S, right? Isn't it?
Yes.
So if I correlate between S and Z inverse, so S is equivalent to 1 minus Z inverse, right? Do you agree? This is anyway.
Yes, sir,
KIC.
agree.
Yes. But in the case of forward Euler, GI of S is KIC by S. Now S is equivalent to 1 minus Z inverse by Z inverse. Agree?
Sir, agree, sir, but I am confusing with like KIC and like
KIC,
there it is
because
KIC in
yes. So because we'll get this TS term extra, right? So KIC into TS is KI.
okay.
We are getting this extra TS term.
Okay.
That is going into the gain, but S is equivalent to 1 minus Z inverse by Z inverse. In the case of forward Euler. And if you come into bilinear transformation, S is equivalent to 1 minus Z inverse by 1 plus Z inverse.
Sir, are you
Into Z.
like combining that KIC with KI or something else?
Yes.
Like I'm
Of course,
confusing a bit
So
there.
KIC into TS is KI. I have defined it like that.
Okay, then you are comparing with S and Z domain terms only.
Yes. I'm comparing S with 1 minus Z inverse. So equal S in S domain is equivalent to 1 minus Z inverse in Z domain.
Sir, if we multiply TS with all the KIC, then it will become equal.
Yes. So that TS term will come. For the time being, I'm combining it with the KI. So I'm considering only S with Z domain. So S is equivalent to 1 minus Z inverse in backward Euler. In the case of forward Euler, it will be 1 minus Z inverse by Z inverse. In the case of bilinear transformation, it is 1 minus Z inverse by 1 plus Z inverse.
Sir, the thing I'm confusing is like there will be TS term will be also with a function of Z for
Yes.
S and
It will be there, but for the time being, I'm not considering it.
okay. Okay, sir. Okay, continue.
Because TS term I am writing in KI. KI is nothing but KIC into TS. Here also KI is nothing but
TS is a number only. Like.
yes, KIC into TS. So TS is a number. So I know that if you have given KIC by S, I know it will be KIC into TS by S is what? 1 minus Z inverse by Z inverse. This is my transfer function in GI of Z. So I will write KI into Z inverse by 1 minus Z inverse. Understood, right?
Okay.
So after
Yes,
this,
sir.
okay. So this is the like whatever I have discussed, I have summarized here. So S is 1 minus Z inverse in backward difference. 1 minus Z inverse by Z inverse in forward difference, which is 1 by Z inverse minus 1 or Z minus 1. So this term is coming here in forward difference, and this in bilinear transformation. If you change it to S, Z to S, it is just same thing. So both are equivalent. So now the main question is, why should I, which one should I use? Should I use backward? Yes. Hello.
This table actually represents the representation of integrator in Z domain. Right?
Yes, integrator. We are only talking about integrator. So using integrator, we got a relation from S domain to Z domain. If it is S in S domain, what is its equivalent in Z domain? It will vary depending upon what area we are considering. So in the backward difference, it is this. In the forward difference, it is this. And in the bilinear transformation, it is this. So now the major question is which one we should be using. So one method Sir has explained in the course is, say, if my S domain says sigma is less than 0, which means is the system stable or unstable? Like, is the pole stable or unstable?
Stable.
Yes. So this is equivalent to
Stable.
mod Z less than 1, right?
Yeah.
Yes.
Within the
So
unit set.
yes. So whatever transformation I am considering, this should hold good. So if you consider say backward difference, Z is equals to 1 by 1 minus S, right? So say S is 1 by 1 minus sigma minus j omega. So I have substituted S equal to sigma plus j omega. Now, if mod Z is less than 1, I'll have 1 by 1 minus sigma whole square plus omega square is less than 1, right? Isn't it?
So S square plus this 1 minus sigma square plus omega square.
Yes, isn't it right? So now 1 minus sigma whole square plus omega square is greater than 1. Isn't it?
Yes.
Yes. So now this is greater than or equals to 0.
This first equation 1 by 1 minus sigma whole square plus omega square. From where you are writing this, sir?
Mod Z is less than 1. So mod Z
Okay,
is the
okay.
magnitude. So magnitude of this is this.
Okay. Okay. So we are putting a 1 by 1 minus S.
Yes,
instead of
yes,
Z.
yes, yes. So I got it from this expression, from backward difference. So this is greater than or equal to 0. So I can write 1 minus sigma square is greater than or equal to 1. So when will this happen? When 1 minus sigma is greater than or equal to 1, right? So sigma is what? Less than or equal to 0. Because say 1 minus sigma is there. Say sigma is positive. It will be 1 minus, say sigma is some 0.1. 1 minus 0.1 whole square, which is 0.9 square. It is less than 1, right? So if sigma is negative, it will be increment to 1. So it is greater than 1. So using backward difference, I have proved, so using backward difference, I have proved that if mod Z is less than 1, it says sigma is less than 0, or mod Z is less than or equal to 1, sigma is less than or equal to 0. So it shows that I can use backward difference because it is quite, not quite, it is equivalent to what stability shows in S domain. It is being reflected in Z domain. So I have not done anything. I have substituted it and then solved it and checked whether sigma is coming less than 0 or not for mod Z less than 1. Is that clear?
Sir, like you
Yes,
are
sir.
taking like mod Z is less than 1 and substituting sigma plus j omega in the place of S and
Yes.
checking whether sigma is less than or equal to 0 or not.
Yes. Yes.
Okay. Okay, sir. Clear.
Okay. So so this is the final outcome. So using backward difference, I took mod Z less than 1 and I am checking whether sigma is less than 0 or not. So it is retaining stability, right? So it is retaining stability because whatever mod Z less than 1, it is reflecting as sigma is less than 0. So if I use backward difference, if my system is unstable in S domain, it will show it is unstable in Z domain as well. If it is stable in S domain, it will show unstable in Z domain as well. So I can use backward difference. So backward difference you can use. For forward difference, you have to do. I have not shown because you should do this equation. So you consider Z is equals to S plus 1. If you consider Z equal to S plus 1, and you substitute S equal to sigma plus j omega in this, and consider mod z plus 1. Mod z is less than 1, and check what is the condition. So you will get this condition. I'm not doing, but I want you to do, so please do it, not now, after the session. But this sir has anyway shown the entire detail in his video, so I hope you have gone through that. So this is my equation. So this is not equivalent to sigma less than 0, right? So it is giving me something. So if my system is stable here, it is not exactly telling me that it is stable in S domain. So the stability is not being the same in both S domain and Z domain if I use forward difference. So this method should be avoided. We cannot use forward difference, because if the system is stable in S domain, if we transfer it to Z domain, that's like it still should be telling me that system is stable, but it is not saying that. So that's why we should not use this method. There is less than a minute, so if this meeting ends, please join again. In the case of bilinear transformation also, I'm not showing again, you should do. So in the bilinear transformation, you should consider this z equal to this expression, and then substitute s equal to sigma plus j omega, apply this one, and you will get this expression. So it also retains stability. So what is the final takeaway from this slide is, I can use this one, backward difference I can use, bilinear transformation I can use, forward difference I cannot use. So if we are transferring from S to Z domain, you can use this, you can use this, because it retains
Sir, in a
stability.
way, they are saying the
I hope my screen is visible.
Yes, sir, visible.
sir,
Yes.
in a way, they are saying the sample we are taking should be less than the mean value of the two samples for the controller, for the integral controller to be stable in both Z and S term.
Sorry, can you please repeat?
No, the sample that we are taking
Uh-huh.
should be less than the mean value of mean value between two samples for the integral controller to be stable in both Z
No,
domain and S domain.
that is a different thing. What I'm saying is, if I'm using any mapping between S domain to Z domain, and if my system is unstable in S domain, it should be unstable in Z domain as well, right? Then only the transformation makes sense. But if it is not telling me that, then it does not make sense. So I have considered all the three mapping methods, and then I have substituted S equal to sigma plus j omega, and provided that mod z is less than 1, I'm checking what is the condition that I am getting. If mod z less than 1 implies sigma is less than 0, then it retains stability. But if mod z is less than 1, it is giving me some expression, then that method should be avoided. And here also it is retaining stability. So if I can consider any transformation, I can either consider this transformation or I can consider backward difference transformation.
So for integral controller, forward difference should be avoided.
Yes, not only integrator, we have used integrator to get the relation between S and Z, because it is easy, because integrator is Ki by S, right? So whatever its equivalent will give us information about S to Z domain. That's why we have considered integrator. In general, we should avoid forward difference. We should either consider backward difference or bilinear transformation. Both are good. Is that clear?
Yes, sir.
Okay. So
Okay.
now
Yes, yes.
coming to the ideal PID controller. So whatever PID controller that we are considering, we'll be considering backward difference only. Whatever implementations are is using, we'll be using backward difference because it is somewhat easier. If you go to bilinear, it will be much complex. So anyway, backward is retaining stability. So we'll use backward. So UFS is Kp plus Ki by S plus Kd into S. So what does backward difference is? Backward difference says that S is related to 1 minus Z inverse, right? So I will get Kp as Kp and Ki as Kic into Ts, and this 1 by S means 1 by 1 minus Z inverse. And KDC, we'll get KDC by Ts because we are differentiating with respect to time, we'll get Ts in the denominator. And this S is nothing but 1 minus Z inverse. Now, if I consider this
Sir,
to be
sir,
KP only.
simply what we can say is we have to like from this continuous time to discrete time, we have to replace S with 1 minus Z inverse by TS, right?
Yes, yes,
1 by TS into 1 minus Z inverse, that's the actual
yes,
transformation.
yes.
Okay, okay, sir, okay.
Okay. So now KICTS, I am calling it KID, or say this KPD in digital, and this I am calling KDD. So now this is my final GPID of Z transfer function. So KP is nothing but KPD, and KID is KIC into TS, and KDD is KDC into TS. So this is the final expression. And the implementation is shown out here. So you from this you can get this final expression. So you can just map it one-to-one mapping, and you can get this expression. So this is all about PID controller and the backward difference. Now, one issue is we know that Z is equals to e to the power st, right? So if we are drawing Bode plot, we want say if we are in S domain, if we want Bode plot, we do log, right? And then it becomes logarithmic. But in the case of Z domain, it is becoming exponential. So log of this will become what? Log of Z becomes linear, right? So we are losing the advantage of logarithmic plot. So what they do from Z domain, there is something called W domain. So they convert Z domain to W domain for doing the Bode plot operation. So the main issue, main point is, in the case of Z domain, we are using this logarithmic aspect of Bode plot, for which we need another transform to convert Z into that transform, so that it becomes again linear, not exponential. So that's why we are converting into this W plane, and using this W plane, they will draw the Bode plot. So in the MATLAB also, they will convert this Z domain. If you give a transfer function in Z domain and use the Bode plot command, it will transfer or transform Z domain into W domain into Bode plot, and then it will draw. Because Z domain is in the exponential, and Bode plot makes it linear, but we want logarithmic, right? Bode plot means logarithmic. So that's why they will convert it into another equivalent transformation, so that everything remains stable, like the stability is retained. So using that, now it becomes linear, and now the Bode plot is again logarithmic. So this is just to give some knowledge of how it happens in the MATLAB, like not much aspects, but just keep in mind there is another transformation called W transformation to convert Z domain into again linear, not exponential. So this is exponential, right? Z domain is exponential.
Sir, like, is there any proof like that how we are getting Z equal to 1 plus T by 2 by omega and all?
Yes, actually, this is nothing but S itself. So from the bilinear transformation, you will get the same thing. Say Z is 1 plus, maybe I will go here. Say here, if you get TS term here. So what did I get? I got Ki by S is equivalent to Ki TS by 2 into 1 plus Z inverse by 1 minus Z inverse, right? My S is equivalent to 2 by TS into 1 minus Z inverse by 1 plus Z inverse. So if you remember this expression, 2 by TS 1 minus Z inverse by 1 plus Z inverse. This is the same thing. You multiply this by Z inverse, 2 by T into 1 minus Z inverse by 1 plus Z inverse. Understood?
In the place of S, they are writing W, just it.
Because there is something called rewarping issue. I'm not going into the digital. So if you convert this into, say, first of all, like this is beyond the course. So here there will be multiple such strips. So we have considered one strip from omega s by 2 to minus omega s by 2. So if you consider any point in this region will be equivalent to mod z less than 1. And if you consider mod z less than 1, it will be equivalent to the entire plane. Right, here we are considering a strip from omega s by 2 to minus omega s by 2. It is being converted to z domain, and this is being converted into the entire left half of the plane. And this is not equivalent to this, right? So that's why we are naming it with a different variable double. But this is beyond the course, so this will be discussed in the digital control course. So how it is being affected, all those things. So if you need any further details on this, you visit any NPTEL course on digital control. There they will have this information on any digital control book. But let us not go into the details. So to summarize, like our basic understanding is we will be using S is equivalent to, as you said, 1 by TS into 1 minus Z inverse. So I will be using this, or we will be using this throughout this course. Why we are using this and why only we are using this? For that, we had an like some discussion about forward difference, and then backward difference, and then bilinear. From the discussion, I came to know, or we came to know, that forward cannot be used. I can use this or I can use this. But this is easy. This is much complex. So I am avoiding this and I am only considering this. So just to teach you regarding the transformation, S to Z transformation, we had this discussion. Is that clear till now?
Yes, sir, it is clear.
Okay. The further details of this is beyond of the course. That's why I'm not discussing, but you can go through digital control where they have explained in the NPTEL course, I think by professor from IIT Guwahati. So
Sir,
can...
this third,
Okay.
This W plane is the imaginary plane. Plane of
omega. See, sigma plus J omega. This is omega. This is W. Both are not same. This is W, not omega. If you see,
okay.
our omega is omega. W is different. Okay. So till now,
sorry, not imagine. It is a complex plane of digital domain.
Yes. Sorry.
Sir, this
Sir,
W
like
plane
you
is
are
the complex plane of digital domain, right?
Yes. So W again have a real part as also imaginary part, similar to sigma and J omega, but it is a different representation. W plane.
So W is the complex plane of digital domain, and S is the complex plane of continuous time.
Yes, yes, you can say that. We are transforming it into another domain, which is W domain, and it is also linear. So it also has some real part of W plus J into imaginary part of W. So again, if real part of W is less than 0, then it is stable. So mod Z less than 1, it implies that real part of W is less than 0. So here also the stability will be retained. And there will be proof of why we are using this. So all that proof is beyond this course syllabus, but it is present in the digital control. So in the digital control, they will explain, they will consider n number of strips in this direction, n number of strips in this direction, and they'll prove that each strip will be equivalent to mod Z less than 1. But let us not go into that. Our main understanding is, if a system is stable, sigma is less than 0, mod Z is less than 1. And we have derived that this transformation retains stability. So we are going with this stability. In Bode plot, we want the logarithmic scale, but Z is exponential. So we are converting it into another equivalent transformation W, which is linear, so that I can again get logarithmic Bode plot. So that is all needed for this course. The details, if you are interested, you can go through the digital control course.
Sir, it is by you are suggesting one IIT Guwahati professor name, please.
I am not exactly sure about that professor name. So when I was doing the digital control course, I was referring to that ma'am. Actually, it was by a ma'am and a professor and another guy. So I don't remember the name. So you just check digital control course now. But it is not necessary or mandatory for you to go into the details of this because it is again another vast topic of different concepts. But if you are interested, you can go, but it is not mandatory, not necessary, and we will not also use W plane in our upcoming lectures. So this is just to give some information of how it will be transformed into W plane. So this information, whatever S is equals to 1 by TS 1 minus Z inverse, is sufficient for this course. So don't go into further details unless it will make things complex. If you are interested, you feel free to go into this additional content.
Okay, sir. Thank you.
So now we have discussed continuous time to discrete time transformations, and we are considered 3 transformations, and we are going ahead with the backward transformation. So now we'll discuss PID tuning of voltage mode buck converter. First, I will show the analog part, how analog tuning is done, and then we'll go into digital part. So we'll be now considering continuous time with delay only. So our digital design will consider continuous time with the delay model. Our analog will consider only continuous time. So now you can correlate with it, what that extra delay term does, how will it affect our system. So coming to PID tuning of voltage mode control buck converter, we know this loop transfer function, controller, modulator gain, and duty ratio to output voltage or control to output transfer function. These are the output impedance transfer function, and this is the audio susceptibility transfer function. But we are considering about K loop of S. So K loop of S is what? K loop is GC into FM into GVD. So this is the expression of this. So this is my GC, and this entire thing is my GVD. So you should be knowing these expressions, because if I ask you to design a controller, you should know these expressions. So what is alpha, all these expressions? So omega ESR is 1 by RC into C. Omega naught is R plus RE. RE equivalent means RE, this is RE. RE equivalent means R on resistance plus RL of the inductor by R plus RC of the capacitor into this expression. So the derivation of these expressions is not mandatory. You just have to know these expressions, which is what. If you want the derivation, then you have to go to the previous course. But the exact derivation is not necessary, but you should have an idea of how they are deriving it. So this is my K loop of S. And GC, this is continuous time, right? So we are in the analog domain. So Kp plus Ki by S plus Kd S by tau ds plus 1. If you take the denominator common and write everything in the numerator, we will get this expression. Sorry. So
Sir, the GVD is a plant model, right?
yes, yeah. GVD is a plant. The plant transfer function.
So, sir,
from
what
duty
is the
ratio to output.
No, sir. Just what is the plant that is some circuit ID?
Yes, currently we are considering buck converter. So this is for the buck
Okay.
converter. So analog voltage mode control of buck converter. Calvin Paul Joseph, who will be taking session tomorrow, he will be doing for boost converter. And for buck and boost, this GVD will
Like,
vary.
sir, GVD in the sense small signal transfer function.
Yes.
Sir, like you have written K loop. Sir, in which lecture exactly will I get this, sir?
You have to refer the small signal transfer functions. Sir has, I think, discussed this in one of the lectures. You just check small signal transfer functions. I don't know if I have put any
Sir, I am
link.
clear
Sorry,
with this
yes.
GVD and
Yes. So in lecture 30, I think Sir has mentioned these details. So the link is given here, embedded. So when I provide this PDF, you can go to lecture 30, or maybe you can note down. So in lecture 30, Sir has provided this. Is that clear?
okay, sir, clear.
Okay. So you just take a common. So denominator is S into tau ds plus 1. So numerator will be what? Kp S into tau ds plus 1 plus Ki into tau ds plus 1 plus Kd into S square. So if I write S square terms together, I will get KD plus KP tau D. And if I write S term, it will be KI tau D plus KP. And if I write constant, it is KI. So if I take KI common, we'll get constant coefficient of the S to the power 0 is 1. And this will be KI tau D plus KP by KI. This is this expression. And the S square coefficient is KD plus KP tau D by KI. So all these things I suggest you to derive. So we are not doing anything. We have taken PID in S domain. We have just added them together. So I'll get numerator function, denominator function. So what is the coefficient in the numerator? They have written. So I have just added it up, segregated S square S to the power 0 coefficient. I have taken KI common. So this is just some normal addition. So I hope you will be able to do. So now, so I am writing this again here.
Sir, could you please repeat? Like K loop is exactly between which and which, like entire loop or
So K
something
loop
there
is
will
this
be.
loop, which is GC into FM into GVD. So this is my GC here, and this is my GVD here, and this is my FM. So K loop is this loop, GC into FM into GVD.
Sir,
Yes.
like there won't be like K loop in the sense it is the transfer function between V reference and V naught. There won't be like that.
No, because there are other aspects like audio susceptibility, because I naught will have a transfer function from I naught to V naught as well. And V will also have transfer function from V into V naught, which is audio susceptibility. So if I consider V reference to V naught, it will be K loop by 1 plus K loop. If I consider I
Sir,
naught to
loop
V
gain
naught,
in the sense. Sir, like
loop,
if I have it, forward transfer function is G and the feedback is H,
it
then
is
you are
GH.
saying loop transfer. Okay, sir.
So this is G. My G is GC, FM, GVD. My H is 1. So GH is GC, FM, GVD.
Okay, sir.
Okay. So I am, whatever PID controller tuning, I am considering pole zero cancellation. So I am cancelling, see, this is my GC and this is my, so GC will be coming here. So this expression GC will be coming here. So what I will be doing, I will be cancelling this pole with this, sorry, this 0 with this pole. And if I change the color, this 2 poles with these 2 poles. So if I cancel them, what I will get? I will get tau D is what? 1 by omega ESR, right? You agree? S coefficient is 1 by omega ESR. Here S coefficient is tau D. So both should be equal. Then only these two will get cancelled.
Hello,
Hello. Hello, is this clear? Okay. So ESR is what? 1 by omega ESR. ESR is what? 1 by omega ESR is 1
Sir,
by
how you are
R0.
cancelling it, sir?
I'm cancelling this one with this. And when will this be cancelled? Tau D should be equal to 1 by omega ESR, right?
Yes, sir. Suppose we have designed a controller, then you have to keep the delay like a TD is
TD is
equal
not delay.
to.
TD is the derivative. TD is not delay. TD is the derivative. T, this is T capital D. So practical PID is KDS by tau ds plus 1. This is not delay. This is the derivative time constant, because KDS cannot be implemented in real life. So there has to be another pole with very less value, which is tau capital D. So this is tau capital D, not small d.
Sir, like how we are cancelling TDS plus 1 to 1 by 1 plus S by omega S here.
I can cancel it when this happens, right?
Yes.
Yes. So here, what are my unknowns? My unknowns are KP, KI, KD, and tau D. I have to find the KP, KI, KD, tau D expressions so that the pole zero cancellation will happen. So I am cancelling this 0 with this pole. So tau D should be 1 by omega ESR. And my omega
Sir,
ESR is,
exactly like Okay,
Yes.
okay. Omega is sir is okay.
Okay, so if I put it here, I will get what? Tau d is RCC, right? Tau d is RC into C, isn't it?
Mm.
Yes. Now, what is the
Yes.
coefficient of S? Q omega naught. And what is the coefficient of S? K1. So K1 should be equal to 1 by Q omega naught. And what is the coefficient of S square? 1 by omega naught square. Here, K2. So K2 should be 1 by omega naught square. Now, what are the unknowns I got? I have, let me use different color. I found tau d, I found K1, I found K2. Only Ki is left, right? But if you consider K loop of S, that this denominator is completely gone, this numerator is completely gone. In GC, the numerator is gone, the denominator is gone. What is left? Fm into Vn by alpha is left, and in GC, Ki is left. Agree?
Yes.
Yes, yes. So I want my loop transfer function to have a bandwidth omega c. So what does that mean? So K loop of j omega c is equal to 1, right? At omega c is the bandwidth. At that frequency, magnitude should be 1. So Fm V in Ki by alpha as I'm putting omega c is equals to 1. So from here I will get Ki to be alpha omega c by Fm into Vn. Isn't it?
Okay.
Vm is what? 1 by Fm. So omega c alpha by V in Fm is equal to omega c alpha Vm by Vn. Because omega c is, Fm is 1 by Vm. So from here, we are getting this expression. Okay.
Sir, the thing what I observed in our organization is like they calculate actually all these,
Okay.
but at the end they still continue to tune.
Yes, yes. So one issue with the pole zero cancellation is perfect pole zero cancellation can never be possible because we are relying on ESR, this LC values, right? But whatever we consider and whatever the values that are there in the hardware, they might deviate. So pole zero cancellation will not work exactly, but it will like the pole and zero are quite close to each other, but they can never be cancelled with each other. So this will just give you a way to design the controller. So to achieve this bandwidth and phase margin, say your bandwidth you want say your bandwidth if you want 50 kilohertz and phase margin you got 45 degrees. But after you have designed GC and you got 49 kilohertz and say 40 degrees phase margin, say for suppose, then you have to fine tune it accordingly, so such that this will be met. Understood? So the pole zero cancellation or all these things will give you some aspect or some procedure or some guidelines to design the controller, but exact pole zero cancellation will not happen. So that issue is always there, and maybe in your case that desired transient response is not being met, and if they want to improve it and they are fine tuning, but if I do not know anything about kp ka kd tau d, which value shall I choose? Shall I choose kp5 or ka to be 10 to the power minus 6? I will not have any idea. So this pole zero cancellation will give me some idea of some kp ka kd tau d values. First I'll put those values and check the response. If I'm not satisfied, then I tune the values around those values to get some better response. But in order to go to that values, I have to use some design and some guidelines. So for that, we are using pole zero cancellation.
Okay, sir.
Okay. So actually this pole zero cancellation will take us closer to the required value of KPK.
Yes, say the pole is here, maybe the zero will be here. Exact pole zero cancellation will never happen because we are not exactly sure about omega ESR. We are saying RC into C. RC will not know. We'll assume it to be few milliohms, but exact location will never know. So exact pole zero cancellation will never happen. But we try to whatever design we are doing, we'll keep the zero close to pole. So it is almost cancelling with each other, because if they're close to each other, then it is almost cancelling, not exactly cancelling. So that is the thing. Now, how do I define Ki? I will define omega c. So omega c is what? 1/10 of the switching frequency. So I'll consider 2 pi fSW by 10 equal to omega c. I will substitute it here. I will get Ki and I will get K1, K2, Kd, sorry, K1, K2, K tau d. So which gives me my GC transfer function. So using the pole
Sir,
zero
I don't
cancellation,
understand why 1/10.
because continuous time model, right? It is also valid till fSW by 10. So the model itself is not valid beyond fSW by 10. So you cannot use this model to achieve higher bandwidth because the model is not valid. So if you are using this small signal model, all these are small signal transfer functions, right? If you are using these small signal transfer functions, which are valid till fSW by 10, so the maximum bandwidth that you can aim to is fSW by 10 because the model itself is not valid.
Sir,
Understood?
like you are saying that the perturbation must be if it is beyond the 1/10th of switching frequency, it may not hold good, right?
No, no, not the perturbation. I'm saying, say I am designing a controller and I have some bandwidth in my mind. Say, you have some model and you want to predict something, but you know that this model is not valid, say after some frequency. Then you cannot, if the model itself is not valid, then you cannot use this model after that certain frequency, right? So in the similar way, the continuous time model is valid till fSW by 10. So whatever you do, you have to do within this bandwidth only. So the maximum, see, bandwidth means the speed of the response. We want the response to be as fast as possible. So we are choosing the maximum bandwidth or the maximum frequency till the model is valid. So the maximum frequency until which this is valid is 2 pi fSW by 10. So we are considering that frequency. But beyond this, the
I
model
want,
itself is not valid.
like you are saying that for greater than 0.1 fSW, it won't valid or
The model is not valid.
not valid for greater than 0.1 fSW. If I
Yes,
want for fSW by 100, then
it is
what should I
valid.
do, sir?
It is valid, right? It is less than fSW by 100. You can use this model.
Okay. If I want fSW,
You cannot use this.
like then what should I do then?
You should go for
Like I
large
want
signal
higher
delay.
bandwidth. Okay.
That we'll be discussing in today, but I don't know. I think we are running late today. Maybe I cannot discuss this large signal delay. We'll see. So this is omega c and ki. So first we'll choose omega c, then we get ki, we'll get k1, k2, tau d. We substitute in GC, we got the transfer function. So this is all about analog. Now, again, it is in lecture 30. So if you want further details, you can go to this lecture. Now, if I
So
consider
this
digital,
FM equal to 1 by VM.
yes, FM is 1 by VM, which is the modulator gain. So yeah,
Okay.
either you write VM
So,
or
sir,
1 by FM.
why this is we are equating this KI equation with the one we have found.
We are equating the K
This K
equation.
omega c with the one alpha omega c by FMVN. Sir, why we are doing this, sir?
Because my bandwidth means at that frequency, the loop transfer function magnitude is 1, right?
Okay.
So I have substituted that and I got this expression. Now,
Okay.
in the case of digital, I am using continuous time with delay, right? So the entire transfer, like the loop diagram remains same except e to the power minus s tau d, except e to the power minus s tau d. Everything is remains same. GC is same. So if I am doing pole zero cancellation, I am still cancelling the, maybe I'll use a different color, which I have not used, maybe yellow. So I am cancelling these zeros with these poles and this zero with this pole. So even if there is a term extra e to the power minus s tau d, which I am not cancelling it with anything. So I am still cancelling this with this one and this with this one. So still my equations hold true, right? These three equations will hold good, right?
Yeah.
Yes. So I am directly writing those equations. But where does this e to the power minus s tau d come into picture? It will come into picture in the phase. Because e to the power minus s tau d magnitude is what? 1. So if I consider k loop of s, then it will not have any effect. See, if I take mod k loop of j omega, then I'll get fm v in ki by s into omega c into 1 is equal to 1 because I have considered omega c. So whatever ki expression I'll get will be similar to this expression only. So whatever I am getting here, everything will be same. What is the difference? Phase margin. Because if I have a function k or say a by s, what is the phase margin? 90 degrees. And if I have a by s into e to the power minus s tau d, I'll get 90 degrees minus that omega into tau d. But phase margin is calculated at gain crossover frequency, which is the bandwidth. So it will be omega c t tau d. So everything is remains same. All the gains are same. Only phase margin will be lesser. That is the only difference in the case of digital, right? So
Sir, like, sir, omega c into tau d is in radians, I guess.
you have to convert this into degrees.
Okay.
Like this representation is omega c tau d, but equivalent you have to convert it in degrees. Yeah, good question. Thanks for pointing out. So the expression is omega c tau d, but as you know, this is 90 degrees, so this should also be 90 degrees. I mean degrees in terms of degrees. So Ka expression, whatever we got from the analog model, the same expression we are getting here, because whatever extra delay term is not coming, extra delay term is coming, that will not alter any K1, K2 tau d. So this is same, this is same, this is same, this is same. What is the difference? Phase margin is the only difference. Okay, so that's why I told when I said that continuous time with delay model is easy to use. See, I don't see any difference between analog and digital because everything is same except the phase margin. So I don't have to do anything new. As this model is valid till FSW by 10, I'll consider this model, which will make my life simpler because I'm not learning something very new or complex. I'm using all the knowledge that I already had, but I'm adding this extra delay which will affect the phase margin. So just to summarize, I got K1, K2 tau d expression. This is my K loop. This is my phase margin. So what are the guidelines to be followed? So the guidelines is first choose omega c to be 2 pi FSW by 10. So now if you got omega c, then you can calculate phase margin. So you have to calculate the phase margin. What is the phase margin? If my phase margin is greater than 60 degrees, okay. If my phase margin is less than 60 degrees, if my phase margin is less than 60 degrees, what shall I do? I will reduce my omega c. Right. I will reduce my omega c so that my phase margin will increase. So I have considered 2 pi FSW by 10. Maybe I'll consider 2 pi FSW by 15. Somewhat lesser, and I'll check if my phase margin is greater than 60 degrees. So if my phase margin is less than 60 degrees, I'll reduce omega c. But if my phase margin is fine, then I'll substitute that omega c here, and I'll compute ki, and then I'll compute kp and as well as kd. Now I got kp, ki, kd in analog domain. So what are the KPD, KID, KDD? So KPD is same as KP, and KID is KI into TS, and KDD will be KD by TS. So this is my digital. So what
Sir, why
exactly?
phase margin you are saying around 60 degrees?
So usually when we consider it, we consider it as a thumb rule. So 45 degrees phase margin, 60 degrees. This is a thumb rule that is followed in practice. So phase margin in this region should be good enough. You don't have to like phase margin less than 45 degrees is not considered as a good design. Phase margin greater than 60 degrees is kind of overcompensated, but still okay. But this should be at least the phase margin should be in 45-60 degrees, because this is 90 degrees minus omega c tau d. This omega c tau d will not be that much big value, so your phase margin will be greater than 60 degrees. In this case, you can consider phase margin to be greater than 60 degrees. But in some cases, phase margin between 45 to 60 is fine. If you consider boost converter, then there will be some issue, and in that case 45 to 60 is fine. But this is a thumb rule that is followed in every design. So in any if you say motor or any drives, if they design a controller, they design a controller such that this phase margin is met. This is a thumb rule, so we follow this. So what we are doing, we are getting all the equations from the continuous time model, and that additional delay is coming in phase margin. So we are just making sure that phase margin is greater than 60 degrees, and we are proceeding with our controller design. Yes, there is less than a minute. If this
So
meeting
here we
ends,
are
please
changing
join
the phase
again.
margin. Here this phase margin is controlled by this FSW, right?
Yes, so whatever omega c that you choose, that is directly affecting the phase margin. If this meeting ends, please join again. There is less than a minute. So this,
Like which lecture should I prefer? Like last week videos are mandatory.
yes, so here I have mentioned this. I think I have mentioned here. Sorry, not here. In the previous lecture. So lecture 30. So this is the lecture where Sarah has discussed, and it has link. So if you click on this text, it will take you to that YouTube video. So you can check it there.
Like, but for this week, like I need to go with the fourth week lectures too. Like I missed last 27, 28, 29, 30.
No. This is not a good thing. See, whatever SAR discusses in week 5 or say week 6, say week 5, it needs the information that is covered in 4, 3, 2, and 1, because it is incremental, right? So to summarize, in week 2, we have discussed about different architectures and sampling methods. And in week 3, we did the MATLAB simulation of this week 3, right? Sorry, MATLAB simulations are of week 2 are discussed in week 3. So until you go to week 2, you will not know about week 3. And week 4, we have learned about different small signal continuous time models with delay and discrete time model, which we are using in week 5 to design controller. If you do not know about this week 4 models, you will not know, or you will face difficulty in week 5. So this is an incremental. So as the weeks increases, your knowledge should increase, right? So whatever that has been covered in the previous week will be like on top of that, we discuss something new. So if you do not, if you have not gone through those lectures, it would be difficult for you to understand, because whatever I'm saying now, maybe you might not even be able to understand. So like, see, I'll tell you one thing. Whatever these sessions are there, these sessions are like, we are taking these sessions to help you to mainly solve the problems. Our intention is to solve few problems, as well as clear some conceptual issues. If you have any few concepts, or like if you have any doubts, if you have gone through the videos, you might have some doubts, and some concepts might not be clear. Maybe you have understood, but you are not exactly sure why this is happening or why that is happening. If you have gone through the videos and if you have some doubts, I can discuss the doubts, and then we can go into the problem solving sessions. But if you consider this as a teaching, here I am not teaching because SAR is there to teach. I am not here to teach, because whatever I will be discussing, that is a subset of what SAR is teaching, or subset of what such knowledge is there. So this is actually not for teaching. So before joining this session, it is expected that you go through all the lectures. On top of that, if you have doubts, then we'll discuss the concepts, and then we'll solve the problems. Because if it is the other way around, then I will be trying to teach, because see, SAR is teaching 10 lectures, right, in a week. Each is, say, how many minutes? 20 minutes, or roughly 20 minutes. So it is around 200-minute lectures. So each week SAR is taking around 3 hours plus to discuss the concepts. So I have how many hours? 2 hours. in 2 hours, I can never cover this much concepts. Whatever I will be doing, I will do to clarify your doubts, your queries, and solving problems. But if you expect me to teach all the concepts that Sir has covered in a week, and if you expect me to cover in a like 2 hour session, it will not be possible for me to explain you, and it will neither be possible for you to understand. So I request you to go through all the lectures before attending this session. And see, I was planning to only summarize, but if I start teaching, then there are so many slides that I'm yet to cover in this session, and we will not discuss that. And in the next week, again, if you have those doubts, we cannot cover because I have to discuss week 5, which is ADC, sensing, all those things. So like I'm telling this to all the students, but today students have not come, but so I'm telling you. If you are not sure about week 4, you will definitely face issue with the week 5. So whatever I am telling may not be, you might not be able to understand. So that will cause issues. So this is for your benefit only. So you should somehow spend time and go through the lectures and cover this delay, because else this delay will get added up. It will be difficult for you to understand the upcoming concepts. I hope you understand. And like these sessions
sir,
are mainly to clear queries and solve problems. I will discuss concepts. See, if you have doubts in controller tuning, I can discuss. But if you have not gone through the entire week, then whatever I'll be discussing today, you will face difficulty. So that would be difficult for you, because you will this session is try to help you, right? Because you will have doubts and you cannot ask sir, right? So that's why we are there to help you. But if you consider this as your source of teaching, then that would be a mistake, and it will neither help me to help you, or it will neither help you. So teaching part completely rely on sir. This is for conceptual understanding and solving problems, because if I only solve problems in this session, and if you have issues, then there is no point of solving problems, because you are not exactly clear with the concepts. So that's why I was planning to give a summary of concepts and then solve the problems. So this is all about tuning in the voltage mode control. And now, so see what happens is like there are many aspects that I was planning to cover in this session, and I will be forcefully it will force me to skip some of the key concepts. So it will affect you, because those concepts are necessary for you, and if I don't get enough time, then it would be difficult for you to understand. So the whatever approach that we have considered till now, it is pole zero cancellation. There is some other approach called alternative approach. Here what we do, see, if you consider the capacitor dynamics, so C dV by dt is IL minus I naught. So if you apply Laplace transform, it will be CS into V naught per term equal to IL per term minus I naught per term. So in the case of current mode control, we have load feed forward, right? Load feed forward. So if you consider V naught per term of S, it will be some fraction 1 by C into IL per term minus I naught per term of S. So in order to act something like load feed forward, there is a gain of 1 by C. So if you want to like act like a voltage derivative, so if you have like, see, I am bringing this 1 by L here. So this is like a voltage feed forward, right? So this is the current information. This current information can act like a derivative on voltage if the gain is C. So this CS is like a derivative, right? So KD into S. If you compare it this with this, we'll get KD to be C. But KD keeping C is a very high value, and it will like absorb a lot of noise. So we'll take a fraction of C. So what we are exactly doing is, how we are getting KD, similar to current mode control with load feed forward. I am considering similar thing as voltage derivative, because this is voltage mode control, not current mode control. I am trying to achieve similar thing by considering this equation, and this equation says my KD is C, but KD equal to C is a very high value and it will lead to so much of noise. So I am considering a fraction of C. So I am considering 0.1. You are free to consider 0.2 as well. So we are considering a fraction of C. So you can start with 0.1 C if you are not like I would say this, if this is not sufficient, if you want to dampen it more, you can increase to 0.2 C, 0.3 C. So again, this is not, it will not give you the exact value, it will give you the direction in which you should go. So now I know it should be a fraction of C, so I'll start with 0.1 C. If I'm not fine with that, I'll go to 0.2 C. And tau d is a small constant, so it can be t by 2 or t by 10. You are free to consider any t by 10 or t by 2. Now Ki is coming from this previous method. So whatever previous method we have, so what is the expression of Ki? So Ki is omega c alpha Vm by Vn. Omega c alpha Vm by Vn. Say if I consider omega c to be 2 pi fSW by 10. 2 pi fSW alpha Vm by 10 Vin. If I consider 20, then whatever expression that SAR has used, you will get that expression. Again, this is not the value. This is just to give you a direction. You are free to consider 10 also. So 10 is the maximum because FSW by 10. So this is the maximum value, but SAR has considered 20 because SAR was starting from very low value, and then if it is not fine, if SAR wants some more integrative action, then SAR will increase. So I got Kp, I got tau d, I got Ki. So just not the exact values, just an approximate, or it will just give you the direction in which you have to go. And how do I find Kp? I find Kp in such a way that my gain crossover frequency becomes 2 pi fSW by 10. So what SAR was doing is, SAR got Kd, SAR got tau d, SAR got Ki. Then in the loop transfer function, K loop of S, that we got in this this expression. So everything is known, only Kp is unknown. So SAR is choosing Kp manual tuning. Say SAR starts with Kp 5 and C, and SAR will increase it to 10 and then C, and SAR will increase it to 15 and then C. So in this way, we are deciding the Kp. So Kd and tau d and Ki, we are getting some way or some direction in which we have to go. So we will be taking some values, and then Kp will tune in such a way that gain crossover frequency becomes 2 pi fSW by 10. So now SAR got Kp, Ki, tau d. So the advantage of this method is because of this derivative action, it will act like a current mode control with load feed forward. So because of this, the transient response will be much improved. So the transient response, the transient response will be improved. So till this point, is it somewhat clear for you how we are choosing these gains? Hello.
Sir,
Sir,
sir.
this is
Okay. So this is all about voltage mode control. So in voltage mode control, we have discussed two things. One is the analog with continuous time model, and digital with continuous time with delay model. So in this PID controller activity, again, we have discussed two things. One is pole zero cancellation, and one is something called alternate method. So in alternate method, we have mimicked, or we have chosen gain in such a way that the derivative term will act as if it is load feed forward in current mode control. So from that expression, load feed forward in current mode control. So from that expression, we know that it should be a fraction of capacitance. And to start with, 0.1c we have considered, and Ki is whatever we are getting from pole 0, and Kp is chosen such a way that bandwidth omega c is 2 pi fSW by 10. So this is like a summary. In again PI tuning of current mode control under buck converter, we are again will be considering analog as well as mixed signal. So first here we'll be discussing analog means only continuous time, and mixed signal means continuous time with delay. So whatever we have considered in the past few slides, the same thing we'll be considering. So this is continuous time model, this is continuous time model with some delay. Now, PI tuning of current mode control with buck converter. So everything is same except here we have GVC instead of GVD. So this is control GVC, not GVD, right? So K loop of S is simply GC into GVC. So this is my GC. Sorry, this is my GVC. And into GC. So GC is my PI controller. No derivative because this needs only PI controller and PI is sufficient. So omega ESR is 1 by RC into C, and omega P is 1 by R plus RC into C. So I have omega GVC, I have GC. So what is GC? Again, sir has discussed this in the previous course, lecture number 38. If you are not sure, you can go through that lecture. Now, GC is what? Kp plus Ki by S, which I am writing as, say, if I take Ki, so if I write this, I'll get Kps plus Ki by S. And if I take Ki by S common, I'll have what? 1 plus S by Ki by Kp. So my omega Cz is what? Ki by Kp. Now, if I am performing pole 0 cancellation, what pole and what 0 I have? I have one pole here, 1 0 here. So what is my expression? My expression is omega Cz is equals to omega P. Right. So omega Cz is what? Ki by Kp. And omega P is what? I'll get it from here. 1 by R plus RC. Say RC, you neglect, you consider this to be nearly equal to R. Because RC is very small. For the ease again, if you want to consider, you are free to consider. For ease of or for simplicity, I'm considering it RC. So Ki by Kp is equals to RC. Now from this I will get Ki is, so 1 by RC, right? So sorry, 1 by RC. So my Kp is equals to Ki into RC, which I am getting it here. Now, what will be my K loop of S? My K loop of S will have R, GC, the numerator is cancelled, Ki and S. My K loop of S is RKi by S. So again at crossover frequency, magnitude is 1. So RKi by omega C is equals to 1. So my Ki is what? Omega C by R. So as we need only PI controller, the number of unknowns are reduced, and it is much simpler than PID because here the unknowns are only 2 unknowns. There we have 4 unknowns. So one equation is Kp equal to Ki into RC. Another equation is K loop is equal to Rki by Ks. From here, we are applying the gain crossover frequency, and we are getting this expression. Now, how do I get Ki? First, you have to again select omega C. This is a small signal model. So 2 pi fSW by 10. And you have to find the Ki. So select omega C, first find Ki. Now you got Ki, then go to Kp and you can calculate Kp. Now you got Ki, Kp, you substitute, you got the controller. And again here phase margin is how much? 90 degrees. We are kind of overcompensating it because phase margin 90 degrees is not necessary, 60 degrees is sufficient. So this is all about analog control. Now if we go into digital control, we have this extra e to the power minus s tau d, right? So everything is same. Additionally, we have this e to the power minus s tau d. So everything is same. So again, this is GVC. So our GVC dash is GVC into e to the power s minus s tau d, which we have been discussing for many weeks now. So everything is remaining same. So I have discussed this will only have effect on phase margin, not on pole zero cancellation. So if we are still performing the pole zero cancellation, whatever values we got, it will be still the same values, right? So Kp is Ki into Rc, and K loop of S will have this extra additional term, and phase margin will have minus omega c tau d, because this e to the power minus h tau d term is affecting phase margin. And my Ki is omega c by R, and my Kp is Ki into Rc, which is the same that we are getting in the analog. So everything is same as analog, except that phase margin will be lesser than what we are supposed to get in analog because of this extra delay term. Now, if I summarize, again, the how am I approaching the PI tuning in mixed signal current mode control Buck converter. So I have these equations which I have written over here. So the same equations I'm mentioning it over here. So in the case of current mode control, Sir has mentioned in the previous course as well. Sir has shown that we can go till FSW by 8. So which is more than FSW by 10, right? So in the case of current mode control, the small signal model is valid, or we can say it is it will be valid till FSW by 8. So we can push the bandwidth till FSW by 8 using this small signal model. So omega c we can consider 2 pi FSW by 8. And again, this is coming from the model validity. So if the model is valid, yes, we can design it. The model itself is not valid, then we cannot design. So the model is valid. So this comes from so whatever small signal transfer function you have, G of S or GVC of S, you push it to higher bandwidth and then actually compare it with the switch simulation. So if it is matching, then we can say it is matching till this frequency. If it is not matching, then we'll say it is not matching. Sir has shown that it is matching, so we can consider omega c. Now, after getting omega c, first should I calculate K? No, first I select the phase margin. If my phase margin is greater than 60 degrees, then I'll fix my omega c. But if it is less than 60 degrees, I will reduce omega c and then check if my phase margin is 60 degrees. But once my phase margin is 60 degrees, then I will fix my omega c and then I'll go to Ki. Now that I got Ki, I will go to Kp. And from this, I will get Kpd is equal to Kp and Kid is equal to Ki into Ts. Is this clear till this point?
Yes, sir.
Okay. Okay, so again, this is mentioned in the lecture 46 of this course. So we have discussed two things. One is PID of Buck and PI of Buck. So the design, whatever results you got, the design is same. First you select omega c, with omega c being the frequency within which the model is valid, which is 1 by 8 for current mode control, and for voltage mode control it is 1 by 10. So after we have selected omega c, we'll choose whether that omega c is leading to phase margin greater than 60 degrees or not. If yes, then we'll proceed to further steps. If it is not, then we'll reduce the omega c and then we'll check again phase margin is 60 degrees. Yes, my phase margin is 60 degrees. First I will compute Ki, then I will compute Kp, Kd in the case of voltage mode control, or only Kp in current mode control. So this is how we design the controller in Buck converter. Now, actually, as today we have spent so much time in the small signal tuning, I might not get much time or no time to discuss time optimal control. So in the case of large signal tuning, we can achieve much faster response than small signal tuning. So this will have a much higher bandwidth or better transient performance, better performance. Because here there is no approximation, there is no question of model validity, because no question of model validity, because we are not approximating anything, no question of model validity. We are considering the actual thing and then designing the controller. So I'll tell you, I don't know whether how much time I have. I think we are already running out of time. So maybe I'll skip this part, but I'll give you a summary of what I was planning to teach. So there is something called trajectory based control. So what we do, we will shape the trajectory. So how you want the current or voltage to follow for a specific transient response. So we will shape the trajectory here. Shape the trajectory. Okay. So, and it is somewhat related to time optimal. So time optimal means it will go to steady state in one switching cycle. One switching cycle. So yes, one thing maybe I can quickly give a glimpse, but if you do not understand, you have to go through SAR's lecture because it would be difficult for me to explain in a like now because we are already running out of time. So what time optimal recovery says is, say this is our first, say we are at here, say I naught comma V naught. Now there is a transient response and then you, so this is called phase portrait. So phase portrait means we'll draw the waveform between one state variable and another state variable. So we are considering one state variable to be I naught, another state variable to be V naught. So we are in the steady state V naught, I naught, and there is a transient. So we are moving from I naught, V naught to I naught plus delta I naught, comma V naught. So delta V naught is the additional current that we are giving as transient response. So from here to here, we want the system to go in one switching cycle. So why I'm saying one switching cycle? So this is the on state trajectory. So this is on state trajectory. And this is off state trajectory. So if I consider inductor current loop, sorry, inductor waveform. So during the transient, it will be on and then it will be off and then it reaches steady state. So this is what we call time optimal recovery. Time optimal recovery. Why? Why? Because this is one on state and this is equivalent to this. And this is off state and it is equivalent to this. Say this point, this average is I naught. This average is I naught plus delta I naught. But it is reaching a point which is not I naught, which is not I naught plus delta I naught also. It is reaching some current value, right? Which is say I. And the voltage, if you consider voltage waveform will be something like this. So here the voltage is V naught. Here also the voltage is V naught. But at this location, voltage is some V. So I would say this as I comma V. So you can imagine it like this. So from I naught comma V naught, before going into I naught plus delta I naught comma V naught, it is going through some transient. So in a switching cycle, it is turning on, it is reaching some value of current and then it is falling down. So at this point, the inductor current I comma V or I comma V. So this is time optimal recovery. So within one on state and one off state, it is reaching. So as I have discussed, so inductor current is something like this. So this is the on state and this is the off state. So from here, we can get T1, T2, T3, which Sir has discussed. And also I was planning to discuss today, but as time is limited, I will not go into the details, but this is the optimal time recovery. So we can get these expressions because T1, the height of this triangle is delta I naught, and you know the slope is M1. So delta I naught by the slope gives T1. And this, if you assume I peak, and if you consider this region, I peak by the slope is the time. So I peak by M1 slope is T2, and I peak by the slope M2 is T3. So that's how I get T1, T2, T3. But you might not understand, you might require some time, but I'll just quickly revise it. If you do not understand, first go through SAR's lecture, and then as I upload this in the YouTube, you can come back. So from here, if you get I peak expression, it is M1, T2, M2, T3. So if you write T3 in terms of T2, T3 is what? T3 is M1 by M2 into T2. So that I substitute it here. Now, charge balance. Charge Q1 is the area under this curve, right? So area is half into base is T1, height is delta I naught. So this is my Q1. So if you substitute T1 in this expression, I will get Q1. So Q1 is this region. So if I show it here, so Q1 is this region. Now, if I want Q2, then Q2 is this region. So what is the base? T2 plus T3, half into base T2 plus T3 into height T3. So T2 plus T3, whatever you got, substitute over here. So you will get these expressions. So I know capacitor current average should be 0. So whatever negative area is there, positive area should also be there. So Q1 plus Q2 should be equal to 0. So if you equate that and if you solve for the expression, you will get I peak, and this can, you can derive it, and Sar has derived it. So you can get this expression. I am not showing the derivation as we are running out of time. And I peak, you will get a root D into I naught. If you substitute M2 is V naught by L and M1 plus M2 is V in by L, it will be V naught by V in, which is D. As there is a square root, you will get I peak is root D into I naught. And T1 is delta I naught by M1 because we are getting here. And T2 I peak by M1 and T3 I peak by M2. So now if I want T1 plus T2 plus T3, what is T1 plus T2 plus T3? It is my recovery time. How much time it is taking for my system to recover from this transient to again come back to this position. It is T1 plus T2 plus T3. So after substituting that, you'll get this expression. And what is my ripple? How do I calculate delta V naught? Delta V naught into C is my Q, right? So I am considering either Q1 or Q2. So I am considering C delta V is Q1. And I know the Q1 expression and I know C. So I have to find delta V expression. So if you bring this C over to this point, and if you substitute M1 to be V in minus V naught by L, and then writing in terms of duty ratio, then you will get this expression. You will get this expression. Again, if do you need require all these expressions? No, these are just discussed in the previous session. And even if you do not understand this derivation of the expression, it is fine. But you can go through Sar's lecture. Sar has shown the derivation in this this course as well. I am not going into the derivation, but I am just quickly revising. So why are we discussing all these things? And this is discussed in lecture 48. So why are we discussing all these things? Because if you consider reference transient, we want our recovery time to be small. So what we want capacitance to be smaller, right? And if you consider L to be small, then your ripple will increase. So if you consider L to be small, your ripple will increase. So I need capacitance to be smaller so that my recovery time will be smaller, which means the system is faster. Now, if you come to step load transient is directly proportional to L. So for step load transient, I need L to be small. And it is inversely proportional to C. So I need capacitance to be large so that undershoot should be small, right? So capacitance should be large, L should be small, so that my undershoot is less. But if I consider L small, then what will happen? In case of reference transient, my peak current will be very high. Also, I need large capacitor here. I need small capacitor here, which is also contradictory to each other. So there is this conflict between reference transient as well as load step transient, because whatever requirement or whatever ideal conditions that you require in step load transient will counterattack in, or it will be a drawback in step reference, as well as what is the best condition in step reference transient will be a drawback in step load transient. So like this is the optimal time recovery. Like if we consider optimal transient. This is the like some concepts in this area. So this is again discussed in lecture 48. So why are we discussing this? Because using this concept, we'll do something called trajectory based current mode control, which is again used as PI tuning of buck converter. So whatever we have learned till now is small signal and it has bandwidth issues. Bandwidth is limited because of the model validity. But if you want to break the limits and if you want to achieve higher bandwidth, then you use a large signal based tuning. And it is called trajectory based control. And see, forget about sigma 1, sigma 2. I'll just summarize. So sigma, here we are considering IL and here we are considering V naught. So the equation of this dotted line sigma will be IL minus I reference. So I reference is my steady state point. So this is my steady state with I reference, comma, V reference. So my sigma is IL minus I reference and the gain is considering minus KP or plus KP. So into V0 minus V reference. So this is the equation of my sigma. If it is say V naught minus V reference is what? Minus V error, right? Minus V error. So it is like IL minus I reference is I load current plus or minus KP into V error. This is only when proportional control is there. If you add integrator, then it will be minus KP V error minus KI integral V error plus IL minus I0 is equals to 0. If you multiply it with plus sign, KP into V error plus integral into V error plus I0 minus IL is equals to 0. So this is the equation that we are getting as sigma. So why we are taking sigma? Because I have discussed it should be one on-state trajectory and one off-state trajectory. So this sigma will give me the gain information. So for that gains, so the trajectory will reach from this point to this point, it will hit it, and then in one single off-state trajectory, it will reach my steady state. So it will hit this surface, and where it will hit the surface, that will be decided by the gain of that surface. So we are planning to find the KPKI using this trajectory based control, and this is the time optimal recovery which we have discussed few slides before. Now, in the case of time optimal recovery or the transient, say we are wanting our transient response to come like this, right? So during this transient response, only KP will be active because KI is mainly to make the steady state error to be 0, right? So steady state error to be 0, and we don't want also KI will not affect the transient response. Only KP will affect the transient response. So whatever KI value that we are considering over here, it is coming from the small signal. So previously, if you remember, we have the K expression as omega C by Fm into V in, or omega C into V by V in. So this was the expression of Ki, and omega C, we are considering whatever we got from the small signal, which is 1/10 of switching frequency. The same value we are considering Ki, and Fm is the modulator gain, MC is the ramp compensation, M1 is the rising slope of the inductor current. So now Fm is 1 by MC plus M1 into T. So that is how we got Ki. So substituting this, we got the K expression. How do I get KP expression? For KP expression, say this is V reference comma I01 comma V reference. And it is going to V1 comma I1 or I1 comma V1. And in the offstate trajectory, it is going to I02 comma V reference. So you have to solve the equation. Like you have to say we have AX dot is equals to AX plus BU, right? So you have to use this equation, and IL, say this is X1 and V0, this is X2. So using this equation for on-state trajectory, you will get one equation, and offset trajectory, you will get one equation. So it is moving from I01 to V reference. So here, if you apply this thing, you will get one equation, and here you will get another equation. Solving these two, so there are two equations, two unknowns, right? Solving these two will give you I1 comma V1, and I1 comma V1 is lying on sigma equals to 0, right? So if you substitute I1 comma V1 in this equation, knowing Ki, you can calculate Kp. These proof are given in the lecture 50 of the previous course. So there Sir has clearly mentioned all the details. And there again, there is less than a minute. So if this meeting ends, please join it again. So I'm not showing the proof of this. So if you solve those equations, and it is not mandatory for you to remember the proof also. If you want, you can go through, but if you don't want, you just have to remember the final expression. So this is the final expression of Kp, and whatever Ki that we got, that is this from the small signal. And what is Kn? Kn is the coefficient of I. So what will happen is we'll get these equations if you solve those equations, but it is not mandatory for you to take a note of all the procedure. If you remember the expression, it would be fine. If you want to know how we are getting, then you can go through that lecture I have mentioned in the previous case. And this is Kn. Kn is the coefficient of I naught. So coefficient of I naught is 1. So what happens in the practical scenario is these gains will be very high. Kp will be very high. That much high gain we cannot use. So what we do is you multiply with K attenuation, some factor called K attenuation on both the sides. K attenuation. Now this Kp into K attenuation, you assume it to be some value. Say I want Kp to be 20. So this Kp into K attenuation is 20. So K attenuation is what? Say this is K optimal. Say K optimal. So K optimal into K attenuation I am considering to be 20. Now K attenuation is what? 20 by K optimal, right? Kp optimal. And what is my new Ki? My new Ki is Ki optimal into K attenuation. So and what is my Kn? Kn is the coefficient of I naught. Kn is K attenuation because we are multiplying with K attenuation, and my Ki is Ki attenuation into Ki optimal. So this, from here I am getting Ki optimal. So using the trajectory based, we have solved for the expression of Kp Ki, but these will be very big. And since sigma is equals to 0, sigma into K attenuation will also be 0. So we are multiplying with some constant K attenuation, and whatever final proportional control we are getting, we are fixing it some value. If you want 30, you can fix it to be 30. If you want 10, you can fix it to be 10. We are assuming it some value. And from this, we are back calculating what is that attenuation factor. And from this attenuation factor, I am considering Kn, and then I'm also considering Ki. So with this, we obtained the large signal controller gains. Again, this is discussed in the lecture 49 of the present course, and Sir has shown the MATLAB simulation of how improvement you can see in the transient response compared to the small signal model. And then there is something called digital pulse skipping modulation. And today I will not get time to discuss this, but no, don't worry. During the hardware, when Sir is implementing hardware, Sir will be discussing about the Verilog code of pulse skipping modulation, which is also called as PSM. There I will discuss the architecture. So today the plan was to discuss the architecture, how to digitize it and everything. So we'll not get time. So let it be like that. So we can discuss in, I think, lecture 70 or 80 around. I think around 79 to 80, I guess. Mostly, I'm not sure. I have to check. In this lecture, Sir has discussed the Verilog code. Maybe at that time, we can have some discussion on digital pulse skipping modulation. So just to summarize, this is the analog PSM of buck converter. For digitizing, we digitize this. So we connect ADC for V0, and then we use a digital comparator. This was there in the final lecture 50. So there will be an issue in the case of classical pulse skipping. This is voltage based classical pulse skipping modulation. And there will be issue because of the peak, because here the IL ripple is dependent on Vin. If Vin, not directly, I would say dependent on Vin. If Vin changes, ripple changes. So ripple might also increase. So that's why we use mixed signal peak current mode control ripple. So here we will fix this I reference. We'll fix this I reference. So the peak is fixed, and now the inductor current operates in the TCM. And this remains same. So again, this is the digitization part. So this is the digitization part. And here we are getting QP from this part. Now we would like to fix the peak. So that's why we are modifying only this part, and this is called peak current based. So this is just to give a glimpse. You might not understand. Please go through lecture number 50 of week 5. So this is a simple concept. We'll also discuss this when we talk about the Verilog part. So this completes our discussion. So to summarize, we have discussed S to Z domain transformations. And we have finalized that we are going to proceed with the backward transformation. And after that, we have discussed PID tuning of voltage mode control, 2 methods. One is pole zero and the other one is alternative. And then we have discussed PI controller of current mode control. We have also discussed pole zero, small signal mode. Then we have discussed something called time optimal recovery. And then we have discussed large signal tuning. Of PI controller to achieve faster transient response. And then we have discussed about digital pulse skipping modulation. So the problem solving session, mainly I have given based on the 2 aspects. One is the PI tuning of current mode control using pole zero, and the large signal tuning of PI. I will not solve, but I will explain you how to solve. So the question is as follows. So I have given you a buck converter which is operating under mixed current mode control, and here is the architecture. So V in is given, V reference is given, L is given, capacitor is given, RE, so equivalent resistance is given. So RE is R on plus RL. So this is R on and this is RL. So the summation of this is given, RE. And RC is given, R is given. So R is the load resistance. So V is 1 volt. So R is 0.1. So I naught is 10 ampere. So if I have given you these details, I want you to find the GBC of S, and then using GBC, using pole zero cancellation, I want you to find GC of S to achieve this much bandwidth. And this is small signal model. I would also like you to find GC of S using large signal PI tuning or that trajectory based controller that we have discussed at the end. So so what is the procedure? So first we have to find GVC of S. I know the expression of GVC of S. I know what is omega ESR. I know what is omega P. So substitute these values in this pole and zero, and then back substitute it. Now you got GVC. So now I got GVC. I have to find GC of S. So how do I find GC of S? By pole zero cancellation. So this is my GVC of S. This is my GC of S. So this will get cancelled with this. That will give me omega P is equal to omega CZ. And the other cancellation is this. So sorry, there is no other cancellation. Only one cancellation is there. Omega P equal to omega CZ. So omega CZ is K by Kp, and omega P is 1 by RC. So from there you will get Kp is Ki into RC, and from K loop of S, K loop of S is nothing but RKI by S. So if you equate it to 1 at S equal to omega C, you will get Ki is omega C by R. So from small signal model, I got Ki, I got Kp. So my Kp I know, Ki I know. So now I will get Kp plus Ki by S, right? Which is Gc of S. So I have designed PI controller tuning using small signal model. Now I want a Gc of Z, which is in the digital domain. So I got Kp and Ki using these equations. If I want to go in digital domain, Kpd is Kp. So Gc of Z is what? Gc of Z is Kp plus Ki into T by 1 minus Z inverse. So I was asking for Kp, I was asking for Kid, which is Ki into T. So now you got this from this using this equation, you will get Kpd, Kid. So I have designed using small signal. Now I'll ask you to find using large signal. So large signal also the final expressions I know. So I know Kp. So I'll find Kp, then I'll find Ki. If I want to digitize it, then I'll find Kpd, which is Kp, and then I'll find Kid, which is Ki into Ts. Okay, I'll find this, I'll find this. Now, I have told you one issue that realizing this much gain is not possible. So what I'll do, I'll consider attenuation factor. I assume Kp to be 20, I'll find Ki attenuation, and from there I'll get normal Ki and all the results. So now Kpd is what? Kp, which is 20. And Kid is what? Ki into Ts. So I got Ki. From this, I'll calculate this Kpd and as well as Ki. I know I have went a bit fast at the end because like one issue was you have not gone through the lecture, so it will be difficult for you to understand. But I cannot skip things because after you have gone through the videos, as my video will be available on YouTube, you can go through my video as well. So that's why I have quickly went through all the lectures. So I know you might not be able to understand, but I request you to first go through all the lectures from 41 to 50 thoroughly. So we are in the week 5. So please thoroughly go through these lectures and then you can go through my video, my today's session. My video in today's
So
session.
is there any control under like tuning is available, part is available in the past lectures like 31 to 40?
31 to 40. See, I'll tell you one thing. So when we are developing a course, it like see, we will teach you the things that you do not know. And now that I have taught you some things, on top of it, I'll add some more things, right? So lecture 31 to 40 does not contain any information about controller design, only controller design,
Okay.
but it will contain all the concepts that you need to learn controller design. And now that lecture 41 to 50 contains controller design, we will not discuss controller design in the upcoming weeks. We'll discuss something in addition to controller design. So in lecture 51 to 60, Sir will talk about sensing and everything. And from 61 to other lectures, we'll go into hardware. So lecture 31 to 40 give you an understanding about different models. Small signal continuous time model, continuous time with delay, discrete time, which you can use to design controller.
I'm clear with those models, but I'm not clear about the controller design.
Because you have not gone through the lectures. You should go through the lectures, and before we have the session in the next week, I suggest all the students, maybe they'll be watching the YouTube later. So if you're watching this, I suggest you to go through all the lectures before joining my session. So we can have a clear doubt session. So I just want to make sure my this session is not for teaching. So this session is not for teaching. This session is for clearing your doubts. Of course, if you have doubts, if you want me to teach that concept, I can teach, but don't expect me to teach all the concepts in these 2 hours, what Sir has covered in an entire 10 lectures. It is not possible for me. And even if I try to cover it, you will not be able to understand. So first you have to go through those lectures, and then I'll clear your doubts. If you want, we can have some discussion on particular concepts, and then problem solving session. So
We will try
don't
to
consider
complete the
my
lecture.
sessions as teaching.
Okay, sir. We will try to complete the first lectures before attending the next.
Yes, yes, yes. And please keep that in mind, because like I don't feel good. Like, see, the last parts I had to go very quickly, and that will not help you. And I don't feel good about it either. But I had to do, because I have to upload this for your like, to help you. But you have not gone through, and it will not help you. But I am forced to do that. I don't want to do. I had to take another session, but it will not be possible, right? Because every week I have to take new session on that lecture. So I request you to kindly go through all the lectures before attending my session. So then in that case, I will be able to help you, because I will not feel good if I am not able to help you, because then there is no point of this session, right? So you please go through the lectures. I will try my best to help you understand those sessions, and we can have some good discussion, and we can solve some good problems.
Class is
In
made those ways.
it is like we are facing difficulty in watching those lectures too, sir. Like we are unable to grasp all the concepts against for one 30 minutes of video. I guess it took me 2 days to understand the concepts in this.
Okay, yeah, I can also understand that. See, even if I'm going through SARS 30 minutes lecture, I sometimes will take 1 hour to understand actual thing, because these are very informative, and a lot of
We can't miss
knowledge.
a
Yes, you
point
cannot
too.
expect it to be completed in 30 minutes. I take 1 hour. See, when I was going through SARS lectures in the beginning, in the upcoming weeks, say week 7, I guess, from week 7 or 8, I don't know, 7 or 8, there are lectures about PID controller in Verilog. See, for this part itself, I took many days to actually understand the code till like register level logic. For me to understand this code, it took me few days of time, and I expect that you will also take time. But I know where you will face issues, because I myself have been through the same journey you will be going through. So I know where you will face issue. I know where you will be facing difficulty in understanding. So I'll be there. But at least you should be like, see, in lecture 41, you have spent some amount of time. You are able to understand 50%. Okay, let it be. You just go to lecture 42. Lecture 43, try to understand. If you are stuck with 41, and if you have missed the other lectures, whatever I'll be discussing today, you'll not be able to take much out of it. But if you have gone through this part, maybe you will understand. See, in lecture 41, we have Z inverse, sorry, Z2S domain, right? But if you see in lecture 43, 44, 45, we have never used this. This is just to give you information. Okay, you are stuck with this. Just go through lecture 42. Maybe it is linked in the other lectures, but okay. So again, there are like many things. You have to complete this lectures for your assignment, because you have to submit your assignment, right? If you are stuck at some point, you can approach me. You know my LinkedIn, right? So you can approach me. Some students ask doubts in LinkedIn, so I try to clarify their doubts, or you can mail me. So some students still mail me regarding their doubts. I try to clarify their doubts. But if you're stuck with lecture 41 till my session come, and you have not gone through this lecture, then it will be a big loss for you, and I will also be not able to help you. So you try to understand, spend time on the lectures. These are very informative. I agree. It will take time. I agree. You spend time understanding that. But if you are not able to understand, you either contact me through my mail or LinkedIn. I'll try to help you. But if it needs discussion, then we will discuss that in the meeting. So you keep this aside, you continue with the other lectures. There might be some concepts which might not be needing this lecture to understand. You try to understand those concepts. now you will have a lot of queries. Say you have some queries, and here you have some queries that we'll discuss in our meeting. But if you have not gone through, then like I will face a lot of headache to teach you rather than clearing your doubt session. So teaching is different thing. Clearing doubts is a different thing. Teaching means I have to teach you everything from scratch. I have to teach each and every concepts. Actually, this session was 2 hours, but I am spending extra time because you are needing this extra 2 hours. So I am putting a lot of efforts to help you. So you should also be putting your efforts from the other side. Then only we'll get finally the fruitful product. So I'll try to help you, and say if the session is going till 3 hours, it's okay for me. I'll spend that extra 1 hour to teach you people. But you should also be putting those efforts from the other side, so that whatever session that I'm taking in these 3 hours will be beneficial to you as well as beneficial to me. How is it beneficial to me? Because I am teaching you in this process. I am also learning. I am also developing my teaching skills, and I am trying to help you. And your doubts are getting clear. You are knowing the concepts in a better way, and you can actually visualize the overall thing, what is happening in this. So from week 1 to week 120, you should link everything. So everything is interlinked. Whatever Sar is teaching, it will have some value. If you are not able to see it, I will be there to help you. But please try to put efforts and watch all the videos before coming to next session. And I'll try my best to help you. Yeah. This is not for you two guys, for all the people who will be watching this video, as this will be in YouTube. So they'll be watching this video. So I'm telling this so they'll be aware, because they have missed it. This is the only way I have to put in the video, and when they go through the YouTube, they'll see. So this is for everyone. So I have seen many students have not
Yeah,
come.
we'll do it, sir.
Yes. Yeah, fine. Okay, then
We'll
I'm
do it,
ending
sir.
this.
Next week it will be smooth, sir.
Okay, so
Sir, it
yeah.
is teja2829 Gmail, right, sir?
Sorry, I'll write it again. So it is teja2281@gmail.com. So teja2281@gmail.com. Okay, you ask me, I am there to help you. Maybe I'll be busy that day, but I'll try to reply you on the same day. So instead of waiting for the entire week, you ask me, you try to question me. And you can also ask in the forum. Forum is there. So if you have a number of questions, you ask them. They are there to help you. And if they do not help you, you can ask me. So you have forum, and then you have me, like, to help you. And then Sir will be taking sessions every, I think 2 more sessions are there. So you ask questions, then only we'll be able to help you. See, if you do not ask questions, then we do not know whether you are facing issue or not. So we cannot teach. But you put efforts, you will have a lot of questions. Ask. So your first priority should be you ask in the forum. I am there with the TS are my friends, so I'll talk to them. I'll ask them to solve your queries as soon as possible. So it will be helpful for you to solve assignments, understand the concepts. Then you can ask me, then you can ask Sir, and you can also have some good discussions in meeting. So this is for all the students who are watching this video. You please try to watch all the videos before coming to my session, and we can have doubt session. Of course, I'll be discussing the concepts, but I would like to discuss it, not teach, because teaching will take a lot of time. And it is not a good practice for you to rely on my videos as teaching, because Sir is already teaching. You refer to Sir videos to learn, and my videos to have like a doubt clearing session or a discussion or problem solving session. So with this, we'll end today's session here. Thank you.